Yeah, hi everyone, welcome back. So in this video we will study the characteristics of a BJT. The screen will get better. As of now I am looking a bit dark, but with the time it will look better. Okay, so we are going to study the characteristics of a BJT. Basically we are going to draw VEC versus IC plot. Like when I vary this VEC, how my IC plot would go. But before that we need to understand what will happen if I forward bias my collector junction. So till this point in the last lecture what we were doing, we were either putting zero bias here or we were reverse biasing it. But now I am forward biasing it. What is happening? My base, which is N, connected to negative, P is connected to positive. So now what I am doing, I am forward biasing the collector junction. Emitter junction is as it is. Emitter junction was forward biased as it is. So now what is the scenario? That both emitter junction and collector junction both are forward biased. So previously whatever the job this emitter junction was doing, it will do the same job. What it will do? It will inject the holes. What it will do? It will inject the electron. Depletion width is very small. Electrons will come, they will diffuse. Holes will come, they will diffuse. This depletion width is small. So previously what used to happen? There was good enough electric field. What that electric field would do? That electric field would take up these holes and current would flow. But now what you have done? You have made the forward bias here. So now the depletion width has also become very narrower. Depletion width also has become very narrower. So this electric field, this is also very less now, right? Electric field is also very less. So now this electric field, it can attract some holes. This particular electric field will attract these holes. This is the job of this electric field, but it will not be able to attract as many holes as it was doing in active region. In active region, when it was reverse biased, then the depletion width was very stronger. So it was attracting a lot of holes. So only minute amount of holes it will be able to attract, and because of that some IPC current would flow because of these holes, right? Here two currents were there, IPE and INE. Out of these IPE and INE, this IPE was important. Now IPE became IPC. Along with that, what will happen? There is a forward bias. Depletion width has become narrower. What will happen? Electrons from here, this is having more doping, this is having lesser doping. Electrons from here will diffuse on this side. Holes from here will diffuse on this side. Electrons are diffusing on this side, holes are diffusing in this side. What will happen? If electrons are diffusing on this side, there will be one current flowing in this direction, INC. Are you able to understand this point? Because depletion width has become narrower. So what will happen? Electrons from N plus side will be injected to collector. Because depletion width has become narrower, you are applying the forward bias. If you apply a forward bias, electrons from base will be injected to the collector and then they will start diffusing in this manner. And since they are diffusing, one current would flow in the opposite direction of diffusion. So previously your IC was IPC only, but now it has become IPC minus INC. And the value of this INC, would depend on this VCB. If you increase VCB, that means you are increasing the forward bias. That means more and more electrons will be diffusing, more and more current would flow. So value of INC is depending on this VCB. If this is depending on VCB, that means IC has also become a function of VCB. So this is the first thing that we did not wanted. Along with that, your IC is also going down. If you increase VCB, more and more electrons will be going here. If you more and more electrons will go, more and more current would flow, then INC will keep on increasing. Because INC is increasing, then IC will keep on going down. So as you increase this forward bias, if collector junction forward bias increases, then what happens? IC decreases. One very important fact, okay? We will be using it somewhere. In the characteristics, we will be using it. And in one liner, these kind of questions can be asked. That if you increase the forward bias across the collector junction, then IC value will go up, IC value will go down, it will remain same. So all these things can be asked in the examination. Okay. Second thing, one more thing. Now, what is the scenario in the base? Let's talk about the base. In base, what is happening? This P++ side is injecting some holes, right? This P++ side, because of the forward bias, they are injecting some holes. Here also there is forward bias, no? this P is connected to positive terminal. So here also there is forward bias. So what this P would do? This P would also inject some holes. Although this P plus plus is much larger than P, if it is injecting 4 holes, it will inject only 2 holes, but some holes it will inject. When it was reverse biased or when there was zero bias, then no holes were coming. But now because of the forward bias, holes are coming from the collector to the base. Previously, what was the scenario? Only these holes were there. Only these holes were there. Only these holes were there. So this is how I should make it. So this was the previous scenario. But now these holes have also come into action. That means the concentration of holes has increased in base. As you increase VCB, base gets saturated with holes. So in the base, a lot of holes will get into action. And if there are more holes, then what base will say? Base will say that I am N-type. That means if there are more holes, more recombination I will do. If there were lesser holes, if you are disturbing the equilibrium in less amount, then less recombination would happen. If you are disturbing the equilibrium in more amount, if more and more holes are coming into action, then base will say that I will do them more and more recombination. Because of that, more and more base current would flow. So here what do you see? Base current has increased. Are you able to understand this point? Because of this forward bias, more and more holes are coming from P side to this base. From here as well, in the base, a lot of holes are coming. So base gets saturated with the holes. Because of that, recombination increases. And if recombination is increasing, then what will happen? Battery will supply the electron. Battery will supply the electron. Electron would go upside. And if electrons are going upside, that means this IB current would increase. If recombination increases, then this base current would increase. So because of this forward bias, when I am increasing this forward bias, more and more holes will get into here, more and more recombination will take place, more and more IB we will get. So because of this forward bias, what do you see here? IB is increasing, and because of what? I am saying that I am not disturbing this VB. VB I am not disturbing, I just need to see the effect of this particular guy, VCB. So if I am increasing this VCB, VB is as it is. Like if it was injecting 4 holes, now also it is injecting 4 holes only. But I am changing this guy. So as VCB increases, your IB is increasing, and IC is decreasing. Why? Because more forward bias, that means lesser depletion width. Lesser depletion width means more and more electrons will go here. If more and more electron goes here, that means the current will flow in the opposite direction. Current will flow in the opposite direction. So total collector current is becoming IPC minus INE. Because of that, collector current is going down. And it is very disheartening. Disheartening you can say, or it is not desired. Because what you wanted, IC equals to beta AB. But here IC is not equals to beta AB. Are you able to understand this point or not? Here IC is not equals to beta IB, right? IB is increasing and IC is decreasing. If IC was equals to beta IB, that means IC was proportional to IB. And in the active region, this was happening. Previous, whatever the previous analysis we saw, that where emitter junction was forward biased and this collector junction was reverse biased, right? So that is known as active region. But now here, if both are forward biased, then there is an issue. IC is not equals to beta IB. Along with that, your IC is also depending on VCB. Or can I say that my IC depends on VCE? Can I say in this manner? Because what is VCE? VCE is nothing but VCE I should say, or VEC I should say. VEC I should say. Sorry guys. VEC. Better would be VEC. Because what is VEC? VEC is nothing but VEB this you are calling as VCB. VEB minus VEC we can say. Or like, let's not get confused with the notations and all. Simply, if you are changing this one, that means the potential between emitter and collector is also getting changed. This is fixed. If you are changing this potential, that means the potential between emitter and collector is also getting changed. Very obvious. Very simple thing, right? Very, very straightforward. Nothing confusing there. So yes or no? So eventually this VCB potential, that is changing this IC current, and that I did not want from the starting of the lecture. We have studied for 4 hours, but in the starting of the lecture only I said that this should be function of only VEB. Although it is still a function of VEB, but it is becoming a function of VCB as well. So more things what you can see, that IC current is decreasing, and IB current is increasing, and this is something that we do not want. We always wanted IC should be equals to beta IB, which is not happening here. So this is the analysis of your collector junction being forward biased, and since your base is getting saturated with the holes, that's why, or saturated with the minority charge carriers, in an NPN it would be opposite, it will be saturated with the electrons. You can do the analysis of NPN on your own, right? You will take NPN here, forward bias you will apply, electrons will be injected from here as well, electrons will be injected, base will be filled with the electrons, and then more and more holes will come into action, and more base current would flow. So all the analysis you can do on your own. So base is getting saturated with the holes, that's why it is known as saturation region. Okay, what it is known as saturation region. So base is getting saturated with the minority charge carriers, because of that it is known as saturation region, and the complete theory has been written here. So you can read it in a very good manner. NPN transistor operating is saturation. Both emitter base and collector base junctions are forward biased. The emitter junction injects many holes into the base, and the collector junction also injects many holes from its side. Both junctions being forward biased, the depletion region collapse, and depletion region collapse means like depletion region here also becomes very thin, here also it becomes very thin, like very thin depletion region is there because both are forward biased. So depletion region collapse, and base will become heavily filled with excess minority carriers, because now base contains large number of holes, recombination in the base will increase, therefore the base current will rise. So here the explanation of base current rising has been written. Okay, so theory should be written in a very good manner. This is what I always prefer, because when you read the notes, like in EDC, no matter how much I explain, what happens is that student will be forgetting it. Every time you read EDC, you will feel like that I am studying new subject. This is the beauty of EDC, or you can say not simply a beauty of EDC. So that's why I wrote down more and more theory, so that anytime you read, you will be able to understand everything. Yeah, yes sir, more and more holes are coming into action, more and more recombination is there, more and more base current is there. Sir, from here electrons are going into this particular side. So everything is written. Let's read it out again. The collector base junction, although forward biased, still has a very weak electric field. Because of this weak electric field, some portion, very small portion of emitter injected holes reaches the collector, and because of that IPC current flows, but that is actually very low. When it was reverse bias, at that time this current was pretty good, but now it is forward biased. Since it is forward biased, very less holes from the emitter to base they are reaching, and since they are reaching, look, this value is not changing, this value was depending on VEB. So previously in the active region, if 4 holes were reaching, here 4 holes are only reaching, but in the active region, from 4 holes, 3 holes were going into collector, but now from 4 holes, only 1 hole will go into the collector. So less holes are going into the collector, right? I hope it is clear to you, because of this forward bias. So very small portion of emitter injected holes reaches the collector. Meanwhile, the increased forward bias at the collector causes more electrons to diffuse from base into collector, right? More electrons from the base will be diffusing inside the collector, and this electron current flows opposite to the hole current coming from the emitter. These directions are opposite to each other. IPC and INC are opposite to each other. As the forward bias at the collector increases, the opposite current becomes larger, so the net current decreases. Thus, the relation IC equals to beta IB does not hold. That means IC is not equals to beta IB. So in our analog electronics, again and again I will be saying that in saturation region, IC equals to beta IB is not applicable. Why it is not applicable? You are able to understand now, right? And IC equals to beta IB is applicable in active region. So all this summary we will write down, don't worry about it. Okay. Yeah, one more thing. Now in forward bias, what did I tell you? When we were studying about transients in a diode, at that time I told you, in forward bias you can replace your PN junction with simply a battery with its cut-in voltage. Let's just say it is 0.7 volt, whatever it is, right? So in forward bias we replace our diode with a simple battery, right? So here what you can see, this PN junction is forward bias, this PN junction is forward bias. So BJT is simply working as two forward bias junction. So what do we do in analog electronics? In analog electronics, what we do is that we replace our VCE voltage, the voltage between these two guys. Basically, between emitter and collector, what do you see? Two forward biased diodes are there. PN forward biased and P forward biased. So what do? We take a certain voltage of VEC. So in the examination, what will be mentioned? VEC saturation equals to 0.2 volt or any value they can mention. So they will mention the saturation voltage. That means if your device is forward biased, if your PNP or if your BJT is working in saturation region, then you can fix this voltage between collector and emitter. So in the examination, this particular thing would be written that saturation voltage between collector and emitter is 0.2 volt. So you should be able to understand what is the meaning of it. This is what I am saying. Okay. So that theory has been written. Because all these things we are again going to see in analog electronics, but in analog electronics, I will directly tell you the results. I will directly tell you that IC is equals to not beta IB. There I will say you don't need to worry about that from where it came. From where it came, you will study in EDC. So we are studying in EDC that from where it came. There also I will tell you that VC saturation will be a fixed value. Fixed value. From where it came, you don't need to worry. Okay. Along with that, collector current in active region, collector current in saturation region. Which current will be larger? Of course, this current will be larger. Why this current is larger? Because here, collector current is actually going down. Right? Because why collector current is going down? First thing is that less holes are reaching here. And second thing is that electrons are being diffused towards the collector. Because of that, opposite current is flowing. So, in the saturation region, collector current is minimum. Collector current is minimum in saturation region. So, in analog electronics, I will tell you this fact as well. That always in the active region, your current would be larger than the saturation region. Okay, so this theory has been written because most of the injector carriers recombine in the base. Only a very small fraction reaches the collector terminal. The transistor loses its current gain behavior. Like current gain behavior. What is the meaning of current gain? IC equals to beta IB. That is current gain. Like IB was a very small current, but IC is like IC is equals to beta IB. Beta value, you know that it would be roughly around 100 or it could be infinity as well, whatever it is. We saw the numerical as well, beta value came out to be 74. So beta value is a very large. So if IB is my input current, if I say IB is my input current, then IC will be my output current. So IC is the amplified version of IB. But that is not happening here because IB is increasing, IC is decreasing. Under saturation, the device effectively behaves like a two forward bias diodes, and in circuit analysis, we replace it with a small constant VC saturation voltage rather than treating as a controlled amplifier. So when we use the amplifier, we will operate our BJT in active region, not in saturation region. Okay, so this will be used for amplification. So all these things in analog electronics, I will tell you that your BJT for amplification will be used in active region. Why in active region? You have understood here, right? Because in active region, this was the scenario. But here, this is not the scenario. So BJT in saturation region, why do you use it? As a switch. It can be used as a switch. And which switch? On switch. What is the meaning of on switch? Like I told you, in diode, if it is forward biased, then how you can replace it? Simply like a battery. So it is like a on switch, no? If cut-in voltage is 0, then what will happen? It will simply be short circuited. What is the meaning of on switch? There is any circuitry here. What is the meaning of on switch? On switch means simply short circuit, right? So your BJT in saturation region can be used as a switch. Okay, simply it can be replaced as a battery. So that's why we will use it as a switch in saturation region. Now there is something called cutoff region. What is the meaning of cutoff region? When both are reverse bias. This is also reverse bias, this is also reverse bias. When it was forward bias, what it was doing? It was injecting the holes and those holes were being collected, and because of that we were getting good amount of current. When it was forward biased, when my emitter junction was forward biased, it was injecting the holes were being collected and good amount of current we were getting. But now if it is reverse biased, then what will happen? It will drive very less amount of current. Like first thing is that it will not inject the hole. So that thing is gone. What it will do if it is reverse bias? If it is reverse bias, it will drive very less amount of current. This will also drive very less amount of current. That means whole BJT can work as an off switch. That means the current, IC current, would nearly be 0 or very small saturation current. Reverse saturation current or very small reverse saturation current. So isn't it like PN junction? Isn't it like PN junction which is reverse biased, right? So in saturation region, PN junction being forward biased, this was your saturation region because both were forward biased. If both are forward biased, so this can also be replaced with a small battery. This can also be replaced like a small battery. So that's why it was working as a on switch. But in reverse bias, it will work as a off switch. So if your mode of working is cutoff region means both are reverse bias. Both are reverse bias, then it will drive very less amount of current, so it can work as a off switch. In saturation region, both are forward biased. If both are forward biased, then it is simply like a PN junction which is forward biased, so it can work as a on switch. But if it is in active region, this is forward bias and this is reverse bias, then it can work as amplifier. As of now, you don't know what is amplifier, but a small idea you have got. IC equals to beta IB. This is the amplification scenario, right? IC equals to beta IB, or you can say that this particular current is depending on this VEB. More VEB, more current. So my output current is not depending on this node potential. Like it is not depending on this particular port. It is depending on some other port. So let's just say here I apply some signal. So effect of this particular signal will be reflected here. Look, as of now, you don't know what is small signal. If you have studied analog, then you would know what is small signal. So let's just say this was 5 volt. On this 5 volt, if I am applying 1 millivolt sinusoid wave. So if I change this 1 millivolt sinusoid, like previously it was 5 volt, we were having some IC. Some collector current I was getting. Now if I change this particular voltage by a minute amount, so here also the current would change, right? And that current can be flowing through some resistor and I can get some gain as well. So this particular voltage that I am applying, that can be amplified using this particular current. So that's why we use our BJT in active region for the amplification purpose. What is amplifier? Why do we how do we amplify our signals? Everything you will study when we study our analog electronics chapter. A lot of people would have already studied analog, then they are moving to EDC. So I guess you already know about amplifier and all these things. But actually in analog we focus more on MOSFET. When we study amplifiers, we focus more on MOSFET because nowadays BJT is not used for amplification purpose. For amplification purpose, you use MOSFET. BJT is used in high frequency circuits. Okay, when you study high frequency analysis in analog circuits only, although it is not there in your gate syllabus, but once you go to masters and you opt for proper analog IC design course, so there you will study high frequency circuits. So there you would see that BJT is being used. But for amplification purpose, nowadays we focus on MOSFET. So you would see in our analog course, we have spent 45 hours on MOSFETs, but only 10 hours in BJT. Because you know that last years, like in last 5 years, from BJT, DC questions have come. Like on DC analysis, questions have come, but for amplification, they never asked question on BJT. And even if they had asked, that question can be solved with the concept of MOSFET. So all these things we discuss in our analog electronics course. So there I have completely given like what kind of questions are asked and why they are not asking questions on BJT for amplification. DC analysis they ask, but amplification they don't ask. And whenever they ask amplification, what they do, they give base current equals to 0. And if your base current is 0, your MOSFET becomes BJT only, or your BJT becomes MOSFET only for amplification purpose. Okay, so whatever the question that they have asked for amplification, that can be solved using the concept of MOSFET only. So you don't need to study BJT separately if you already know MOSFET. Like hardly you need 1 hour of effort. So in that manner we have studied. But in gate field, what we have seen is that people spend too much of time on BJT, amplification and all these things, and in MOSFET they would hardly spend 4 to 5 hours, which is wrong actually. Okay, you can see the previous year question paper, like they are asking MOSFET and MOSFET only for amplification. They don't ask BJTs. BJTs they ask for DC analysis, not for amplification. And even if they ask, that question can be solved with MOSFETs. Right? Yeah. So now you have understood our region of operation. First, you understood about the forward biasing this collector region. If I forward bias this collector junction, then what would happen is that my IC current is going down, IB current is going up. It is simply working as a 2 ohm switches, like it is simply working as 2 forward bias diodes. So I can simply replace it as a battery only, or I can say that collector to emitter voltage is fixed. Collector to emitter voltage is nearly fixed. So it is working as a on switch. When both are reverse biased, then very less amount of current would flow, or you can say nearly zero collector current would flow. So it is working as a off switch. But if you want to make on switch, off switch, why would you use BJT? You can make it through that diode only, no? If I want a on switch or if I want a off switch, then what I would do? Do this particular thing. If I want a off switch, then what I would do? Do this particular thing. Why would I use BJT there? So BJT is used for amplification purpose, right? So why it is known as transistor, everything I will tell you. So the name transistor came into action for this particular thing only. Like BJT was not made for this purpose. These purpose we were already able to achieve. On switch, off switch, we are already able to achieve with PN junction. So BJT was not made for this particular purpose. BJT was made for this particular purpose. Okay, and based on this only the BJT name is given. Bipolar, you already know, holes and electrons are both are conducting the current. That's why it is bipolar. But why transistor? So transistor is nothing but a transfer plus resistor. Okay, so we will talk about it. Don't worry, we will talk about it. Let's go to our next topic, which is, so till this point whatever we discussed, that was the setup of this particular topic. What is this topic? This topic is characteristics of a BJT. We will take the case of common emitter. That means we will define all our potentials with respect to emitter. All the potentials will be defined with respect to emitter. That means emitter will be grounded. Now I know one thing, that I want to make it forward biased. If I want to make it forward biased, that means here I need to apply negative potential. Let's just say if emitter is 0 and VB is 2 volt, then this will be minus 2 volt, right? 0 minus 2 volt. So base will be minus 2 volt. So P is connected to 0, N is connected to minus 2 volt. What does that mean? It is forward biased. Now this VEC would decide, this VEC potential would decide whether this junction is forward biased or reverse biased. What I am saying, this potential would decide whether this is forward biased or reverse biased. Here I am not applying any battery, right? Here we are not applying any battery. No battery has been applied here. So no battery is there. But because of the VEC potential, something would happen. So let's get started. I will assume VB is fixed. What we need to do? First, what we need to do? We need to draw VEC versus VEC versus IC for fixed VB. That means I will not be changing this potential. If I am saying that my VB is 2 volt, then it is fixed at 2 volt. So if my VB is fixed at 2 volt, then what will happen? Let's just say initially my VEC will be 0. So I am saying that initially my VEC is 0 volt. I know that, sir, this is forward biased because 2 volt has been applied here. P is connected to 0, N is connected to minus 2 volt. So it is forward biased. What do you talk about what do you talk about collector junction? Emitter junction is forward biased. Emitter junction is forward biased, no doubt about it. What about the collector junction? Is it forward bias? Is it reverse bias? Or your answer is, sir, I cannot tell. What is your answer? It is forward biased only. How? How you can say, sir? VEC is 0 volt. So just consider this particular scenario. This is your PNP. Here you have applied 0 volt. Now you are saying that, sir, here 2 volt has been dropped. On this scenario, 2 volt has been dropped. So here minus 2 has to be dropped. No. Are you able to understand this point? You are saying that, sir, VEB is equals to 2 volt. Now there would be something called VBC as well. VBC should also be there. Now you know that your VEC is equals to VEB plus VBC. Do you agree to this point? VEB plus VBC. Now if VEC is 0, if this is 0 and you are saying that this is 2 volt, then your VBC has to be minus 2 volt. No. Or by simple circuit analysis you can see. On upper side I am applying 0 volt. So between collector and between emitter and collector I want 0 volt. Emitter and collector should be at the same potential. If they are at the same potential, if this is at 0, this is at 0, and you are saying that your base is at minus 2, what does that mean? Here minus 2 has been dropped. No. Are you able to understand this point? This is plus 2, this is minus 2. So basically, if your VEC is 0, then there is a battery which is looking something like this. you are not making it, since VEC is 0, you feel like that, sir, here there is a battery of 2 volt and here there is a battery of minus 2 volt. That means N is connected to negative and P is connected to positive. What does that mean? It has become forward biased. So when your VEC was 0, you wanted it not to become, like, you did not wanted anything, you do not want anything, you don't know what will happen. So what you did, you are changing this VEC with respect to, and with respect to that you need to draw this IC. So first what I did, I have fixed this VEB. VEB is fixed to 2 volt. If VEB is fixed to 2 volt, then what did I show? If I am applying VEC equals to 0, then what is happening is that this is coming under forward biased. And in forward bias, you know that collector current is very minute, because collector current would keep on going down. So although some collector current would be 0, sorry guys, although some collector current would be there, when your VEC is 0, some collector current would be there, but that current we will not show. We will say that, sir, nearly 0 collector current is there. In forward biased, what you have seen? In forward bias, you have seen that, sir, my collector current is continuously going down. My collector current is continuously going down. Some collector current will surely be there. Some collector current will surely be there, but in the books as well you can find, in the NPTEL lecture also you can find that they would show it 0, but always you need to remember, if in some IITs they ask you if there is some collector current, you would say yes sir. When you have applied VEC equals to 0, we will draw IC versus VEC plot. Everyone would remember that particular plot. Very simple plot it is. If you are studying it for the second time, you would already know the plot, but you always used to show 0 current here, but that current is actually not 0. Forward bias. When both are forward bias, that means we are currently running in saturation region. So when we are running in saturation region, there is surely some minute current available. Okay, but although we will show it 0 only. Is that clear to you? Why it is forward bias? Is that clear? Because this complete was 0 volt. If 2 volt is dropped here, then here minus 2 volt has to be dropped. So minus 2 volt means N is connected to negative, P is connected to positive. That means it is forward biased. Now, what I will do? I will increase my VEC. Let's just say I have increased my VEC to 1 volt. If my VEC has become 1 volt, then what do you think? What will be the drop here? The drop here would become 1 volt only. Or let's take as 0.5. If my VEC has become 0.5, from 0 to 0.5 I am coming. So what do you think? What will be the drop here? 1.5 volt. Say yes or no? 0.5 is the total voltage. 2 volt is here. That means minus 1.5 has to be applied here. Very simple thing. Very simple network analysis. If you don't understand network analysis, then do this equation. From here you can understand. But very simple analysis. 0.5 is the total applied. 0.5 is the total applied. You are saying that here I am having 2 volt. That means here minus 1.5 I need to have. Then only 2 minus 1.5 would become 0.5. That means N is connected to negative, P is connected to positive. That means again it is forward biased. But now the forward bias has decreased. Previously, what was the forward bias? We were having the forward bias of 2 volt. Now we are having a forward bias of 1.5 volt. So forward bias has decreased. Here what I have written? As you increase the forward bias, as VCB increases, as you increase the forward bias, IC goes down. Forward bias increases, IC goes down. Forward bias decreases, IC go up. Very simple thing, no? Like if I was having a forward bias of 2 volt, then I was having some IC1 current. Now if I am having a forward bias of 1.5 volt, then I am having some IC2 current. You know that IC2 would be larger than IC1. Because more forward bias, lesser collector current. Less forward bias, more collector current. That means your collector current is increasing. Or let's make it somewhat like this. Your collector current would be not linearly, like somewhat linear you can make. In this manner, your collector current is increasing. Can you tell at what potential your forward bias will be gone? If I apply my VEC equals to 2 volt, then what will happen? On the upper side, you are applying 2 volt, and you are saying that VEB is having 2 volt only. That means this much potential is already 2 volt. That means this potential has to be 0 volt. That means this will simply be shorted. And what is this particular scenario? This particular scenario is nothing but your active region only. From here only we started, no? Right? Do you remember? if I apply VEC equals to 2 volt, this will become 2 volt. That means base and collector has to be shorted. That means there should not be any potential between base and collector. That means forward bias is gone. And in this scenario, what happens? In this scenario, you will get some collector current. Good enough collector current you would get. So this will be that particular scenario. Now if I change my VEC to 2.5 volt, let's just say 2.5 volt. So if I have changed it to 2.5 volt, so let's remove all these things so that you would be better able to understand. So now I am applying 2.5 volt. Here 2 volt has been dropped. That means now how much voltage should be dropped here? 0.5 voltage should be dropped. Because now you can see that 2 and 0.5. What that would be? 2.5. So 2.5 equal. That means N is connected to positive and P is connected to negative. What does that mean? That means now your collector junction has become reverse bias. And I told you this IC current, or here I am showing that IC current, in the emitter junction is forward bias, collector junction is reverse bias. That means this is your active region. And I told you, even if you increase this bias, in the active region, collector current will not be changing much. Because this collector current is a function of this VEB. Do you remember this expression? IC equals to IS e to the power VEB by eta VT minus 1. This was there, this expression was there in active region. This expression was there in active region. So if VEB is fixed, if this VEB is fixed, then IC is fixed. What I am saying is that if VEB is fixed in active region, for active region, if VEB is fixed, then IC is fixed. That means even if you keep on increasing this VC from 2.5, if I go to 3 volt, then this 0.5 volt will go to 1 volt, because 2 plus 1 has to be 3. So even if I increase this reverse bias, even if this reverse bias is being increased, here your emitter junction is already forward biased, I don't care about it. But even if you increase the reverse bias, nothing will happen. Almost the current will remain constant only. Is that clear? So after this point, after this particular point, what this point would be? This point would be, sir, when I have applied VC equals to VB only. This will be your VB. So sir, after this point, nearly current would be constant. So this was the region of saturation. After that we are getting into linear region. Is that clear? So that I did for VB equals to 2 volt. VB equals to 2 volt. This was the scenario done for VB equals to 2 volt. Okay. Now if I change my VB to 4 volt, VB to 4 volt I am changing. How would I start? VC equals to 0. VC equals to 0, that means here, or you can change the polarity of battery. How would you change the polarity of battery? Here, if this is 0 volt, this is 4 volt, so this has to be minus 4 volt. This has to be minus 4 volt. N is connected to negative, P is connected to positive. What does that mean? It is forward bias. Forward bias means lesser current, very less amount of current would flow. That current I would nearly assume to be 0. Although some current would be there, but nearly I would assume to be 0 only. One second. Yeah. So I was saying that the current would be nearly 0. Okay. Sneeze came into action. That's why I had to pause the video. Now what I will do, I will keep on increasing it. Let's just say from 0 to 2 volt it has become. If it has become 0 to 2 volt, then what will happen? Here what we will be having? 2 volt. Right? Reverse bias of 2 volt we will be having. Then, sorry, forward bias of 2 volt we will be having. Forward bias has decreased. If forward bias decreases, then what will happen? Collector current would increase. So if I draw the diagram, collector current would keep on increasing. But collector current would be like very low current would be there. So in some textbook as well, you would find that this kind of graph will not be made, this kind of graph would be made. That means in saturation region, no matter whatever the potential you apply, current is already very low. So you would say, sir, nearly same amount of current would flow, but just tell me one thing. Here I needed to apply 2 volt to get into the active region. So here how much voltage I need to apply? When I apply 4 volt here, then what will happen? This will become 0. That means this will be shorted when I apply 4 volt here. So 4 volt has been dropped here, so this will be shorted. Now if this is shorted, now this is the active region we have achieved. After that, from 4 volt to 5 volt if I go, then this will be 1 volt. The battery polarity would be completely changed. This would become 1 volt, right? N is connected to positive, P is connected to negative. What will happen now? Now, since this is forward bias, this is also forward bias. Sorry, this has become reverse bias. This has become forward bias. So what will happen? It will take up the holes, and because of that, good amount of current would flow. But now, even if you increase this VEC voltage, even if you increase this VEC voltage for 5 to 6 you go, then here reverse bias will be changing from 1 volt to 2 volt. But even if you change this reverse bias, there will not be much impact, because now this IC current is depending on this VEB. IC is depending on this VEB. Okay. Here I needed to apply 2 volt, but now how much I need to apply? I need to apply 4 volt here. So this time I need to apply more potentials. Along with that, my IC current would also be more, no? Like when VB was 2 volt, then equation was IC e to the power 2 by VT minus 1. Now it is 4 volt, so equation would be IS e to the power 4 by VT minus 1. That means current has increased. So this current would be more. So this is for VB equals to 4 volt. And how much potential I needed to apply here? This much potential. Arey bhai. So let's call it VB1. Let's call it VB2. Similarly, if more current, that means more and more current would keep on flowing. If I keep on increasing the potentials, then more and more scenario in this manner, it would keep on going up. So this is the characteristics we will keep on getting. Although this gap will not be same, okay, this gap will not be same. Like if you are doubling the VB potential from 4 to 6 if you are going, so here this is exponential, no? So current would rise up exponentially. More VB means more and more holes will be injected here, more and more holes will be injected here, that means more and more current would be there. But that current would rise up exponentially, right? The current would rise up exponentially. So this gap would be much more. At VB equals to 4 volt, you are having some certain IC voltage, right? Sorry, IC current, some certain IC current you are having. But when you are applying 6 volt, much more current would be there. So this gap would be different, okay? But in the just for showing purpose, we can show it in this manner. All good? All fine? So this is your VB3. So this kind of a graph we will be getting. Now what I do, I remove all this. What if I apply VB to 0 volt? Initially VB 0, VC 0, whole thing is shorted, everything is into equilibrium, so current would be nearly 0 only. This time not nearly 0, this time current would be exactly 0. What I am saying, VB should be fixed, I am fixing it at 0. I am fixing this at 0. Is that clear to you? VB has been fixed at 0. Okay. VEC is also 0. So can you imagine the circuit? 0 volt here, 0 volt here, 0 volt here, everywhere everything is 0. BJT is in equilibrium. 0 bias you have applied. That means this time actual current would be 0 only. Previously all the scenario that we discussed, then when VB equals to 2 volt, 4 volt, 6 volt, at VEC equals to 0, you are saying that current is 0, but what I said, current is not actually 0. Because of the forward bias, some current would be there. Now what will happen? I will increase it. I will increase it to 0.2 volt. What does that mean? Upper side 0.2 volt, this is 0, so this has to be 0.2 volt. All clear? N is connected to positive, P is connected to negative. What does that mean? That means it will straight away come into reverse bias, right? So your collector junction is reverse biased. But this guy is not even injecting holes. Even if it is reverse bias, what is the advantage of it? Because here there is 0 bias, no? VB is 0. What was the job of this bias? This was forward bias. What it was doing? It was injecting holes. Now this hole injection is not even taking place, no? Right? So what will happen? effectively this circuit has become your PN junction under reverse bias, because here there is no bias. That means no holes are coming from here to here. So whatever the reverse bias you apply here, because of that reverse bias, what will happen? Some current would flow. So whatever the current, like here some current would flow, but what that current would be? That current would be nothing but it would be IC, emitter is open circuited, no? This current would be nothing but ICBO. Say yes or no. Do you agree to this point? This current would nothing be but ICBO. Because from here no holes are being injected. Basically towards this side there is no bias. If there is no bias here, only this bias has been applied, which is reverse bias. So it is like PN junction under reverse bias. So in PN junction under reverse bias, such that emitter is under no bias. So how much current would flow? Simply imagine it, no? VB is 0, only reverse bias is there. Because of the reverse bias, what will happen? Electric field will become stronger. Whatever the minority holes are there, they will be drifted. They will be drifting towards the P side. Whatever the minority electrons are there, they will be drifting towards the N side. Because of this drift, some current would come into action, and that current we were calling as ICBO. So when your VB is 0, some current would flow, that is ICBO. Now someone would say that, sir, if I put VB equals to 0 here, then what I will get? Sir, e to the power 0, 1 minus 1, IC should be 0. It is nearly 0 only. Okay? The current would be actually very, very minute. Very, very minute current would be there. Although I am showing it like some amount of current is there, but I think I should show in this manner. That very minute current is flowing. Very, very minute current is flowing. This is the scenario when I applied VB equals to 0 volt. So how much is this current? This current is nothing but ICBO. In this expression, you would feel like that, sir, e to the power 0, that would be 1 minus 1. So a collector current should be 0. But I told you, collector current has two components. Collector current, along with that, ICBO could also be there, ICEO could also be there. Here, which current is flowing? ICBO current is flowing. Because if VC is 0, VB is 0, then there is no current. If you increase VEC, let's just say I have taken it to 0.2 volt. So if it goes to 0.2 volt, then what will happen? Here 0.2 volt is applied. So this becomes under reverse bias. So in reverse bias, whatever the current that flows, that kind of current is flowing here. So that current is flowing here. So this kind of characteristic you will get. This is nothing but ICBO. Okay, all good. So I hope the characteristics are clear. Now let's show the region of operation. Let's remove it. Let's also remove it. Let's also remove it. So what I am doing is that I am making some this kind of line. What this line is representing, can anyone tell? Like before VB1, this was the saturation region. No? Here this was the saturation, and then this became linear. For VB equals to 2 volt, then this was the saturation, then this became linear. For VB equals to 4 volt, then this was the saturation. For VB equals to 3 volt, this was the saturation, and this became linear. So that means this much portion would show the saturation, and this much portion would show linear. Say yes or no? So this kind of line I have made, like it is not looking perfect, but I hope you are able to understand that this line is passing through these points, like till the point they are in saturation region. After that they are in linear region. So this is the line of a linear region. I can use a different color of pen. Linear region. This is your linear region. Here linear, whatever it is, you don't need to call it. So this is my linear region. And can I call this much region as cutoff? Because if I am saying that this is my VB equals to 0, that means downward what I will apply? VB equals to minus 1 volt. I am saying that this is my VB equals to 0, then it is going up, going up, going up. So what if I apply VB equals to minus 1 volt? Then what will happen? emitter junction, I have reverse biased, right? I have reverse biased the emitter junction. Are you able to understand this point? Okay. And then let's just say here this is 0 volt. What will happen then? This is -1, so this has to be +1. If this is 0 volt, this is -1, this has to be +1. That means N is connected to positive, P is connected to negative. That means both are reverse bias. And if both are reverse bias, what does that mean? It is cut off. So this particular region where your VB would be negative, can I call this as cut off? Yes, sir. So in one characteristics, I have shown saturation region as well, linear region as well, and cutoff region as well. Linear, or you call it active. Again and again, I am using linear word. I hope you are not getting confused. You sometimes call it active as well. Active or linear both are same. I am sorry if you got confused here. Okay, active and linear both are same. Is this characteristics clear to you? A lot of people would simply mug it up, but I hope you have understood the deep meaning of it. That why this is saturation, why this is active, why this is cutoff. Why here there is ICPO current. Actually we showed this 0 current, but is it actually 0? No, it is not actually 0. So I hope now when you make these characteristics, I hope you will be able to explain in a better manner, much better manner you will be able to explain. So shall I make another explanation? Shall I explain it again? But let me erase it, whatever it is. So I will explain it, but in a very quicker manner I will explain it. So what we did, first we fixed it. Let's just say it was 2 volt. Applied 0 volt here. Here what came into action? -2 volt came into action. That means both were forward biased. That means you are in saturation region. In saturation region, very minute amount of current would be there. Then suddenly, when you applied VC equals to 2 volt, then what really happened? Here 0 volt came into action. You are in the active region. Now in the active region, you know that this current would simply be depending on this VEB. So now, if this is fixed, then this current is also fixed. Okay. So this kind of characteristic you got. As I increase the VB voltage, what will happen is that more and more collector current would flow, but in the active region. In the saturation region, again, the current would be very less. Let's just say if VB is 4 volt, so VC I need to apply it to 4 volt. When I apply it 4 volt, then what will happen is that this guy would be 0. Again, I will get into active region, but before 4 volt, I will be in the saturation region only. So in this scenario, everything would keep on going. Now, what if I apply VB equals to 0 volt? So when VC is 0, everything is 0 now. Now your device is under equilibrium. Under equilibrium, it will drive 0 ampere current. So previously, I was saying that at VC equals to 0, IC would be 0, but that was not correct. Some minute IC current would be there, even if VC is 0. But now, since I have applied 0 volt at both of the terminals, then now actually the collector current is 0. As I increase this voltage, then forward bias, reverse bias, we are directly getting into active region only. So here I have shown a bit of saturation region, but actually directly we are getting into active region only. Why is that so? Because this is 0 bias, but this is reverse biased. Because of the reverse bias, whatever the reverse bias current that is flowing, that would flow. Because why only reverse bias current? Because actually this emitter is not injecting any holes because of this 0 bias. So that's why very less amount of current would be there, which is known as ICPO current. And before, like below VCB equals to 0, what will happen is that I'm going to apply negative potential, and negative potential means there would be both will be in the reverse bias, and since both are in the reverse bias, then what will happen is that I will be getting 0 current or nearly 0 current. So this particular region would show the cutoff region. This is your active region, this is your saturation region. So this is the complete characteristics. Now one doubt may be arised. What is that doubt? This we have previously discussed as well. Sir, if I increase the reverse bias here, if this reverse bias is being increased, then what will happen, sir? More and more electric field will be there. That means this electric field will pull these holes strongly. That means, sir, IC current should increase. That means IC current is somehow depending on this reverse bias as well. No? Let me repeat the doubt. Sir, if I increase this reverse bias, here whatever the electric field was there, this will become stronger. If this is becoming stronger, then it will pull the holes strongly. That means the recombination that was happening in base. Previously, sir, 5 holes were coming. Now, at a particular reverse bias, 4 holes are getting here. And because of these 4 holes, some current is flowing. But, sir, if I increase this reverse bias, then what will happen? Stronger electric field will be there. This field has become stronger. And since, sir, this field has become stronger, so previously 1 hole was being recombined. Let's just say previously 2 holes were getting recombined. Now, sir, only 1 hole will get recombined and I will get larger current. So somehow, if I am increasing this reverse bias, I am getting a bit more current. So yes, this actually happens, but this is your ideal characteristics. What we have studied? We have studied the ideal characteristics. So whatever your doubt is there, that doubt is actually true. So practically or in non-ideal case, what do you get? Somehow your IC, somehow your collector current would be depending on this VEC voltage, because if you increase the VEC potential, then more and more reverse bias would be here, more and more reverse bias would be here. Then what will happen is that more and more holes they will attract. If they are attracting more and more holes, then somehow a very minute dependence would be there, the current can increase. But in the expression, what do you find? That there is no dependence of VEC. That means this is also your ideal equation. Ideal equation, not a non-ideal equation. Are you able to understand this point? But do I want this? Do I want IC to be a function of this potential? Let's call this potential as BBC. Do I want this? No, I don't want this. How can I stop it? Look, if you increase this reverse bias, then surely this electric field will become stronger. But what if I do that here I do the less doping? Sorry, here I do the more doping and here I do the less doping. So if I have done more doping here, then what kind of depletion width I will be getting? This kind of depletion width I will be getting. Say yes or no. So even though electric field is becoming stronger, but that electric field is becoming much stronger here. In this particular region, there is very less effect of electric field. So even if you are increasing it, there will be very less effect of this electric field in this particular region. So previously, if it was attracting 4 holes, now also it is attracting 4 holes only. Even if you are increasing this reverse bias, increase it. You kept on increasing it, but the effect of that particular electric field was very less here. Like first these holes will come into action from this electric field only, no, whatever the electric field is there. So this electric field will attract these holes. So inside the base, electric field is not changing much because of the increase here. The electric field is changing much here, not inside the base. So inside the base, if electric field is not changing much, that means recombination would be same. Recombination would be same, that means this IB current would be same. If recombination is same, that means IB current is same. You are not changing VCB, that means IE is already same. So if IE is fixed, IB is fixed, then IC will also be fixed. Are you able to connect the dots now? Very, very important point these are. People will say why base is more doped? Because of the fabrication. Absolutely baseless statement. If I am doping the base more, then what is happening? Depletion width is not getting extended towards the base. More and more depletion width is getting extended towards the collector. So if less depletion width is being extended towards the base, then these holes are not depending much on this electric field, and this is what I want. I want that these holes should not be depending on this particular electric field, because if they are depending on this particular electric field, that means they would depend on this particular electric field. If they would depend on this particular electric field, that means current would be controlled by this particular voltage, and that I don't want. I want the current to be controlled by this particular voltage, not by this voltage. So if I make the doping of base more, then the depletion width towards the base will be very less. That means the effect of this reverse bias that I am increasing will not be much impacted by the base region. So in the base region, if previously 2 holes were recombined, now also 2 holes will be recombined. This current remains same, VB is already fixed, this current remains same, IC has to remain same only. But at very higher bias, what may happen is that this can be extended, and since this base will also get some effect of this particular electric field, then what will happen is that now recombination may go down, so IB will go down, IC will go up, and since IC goes up, so now here you are seeing this constant slope, but now this kind of characteristics we will keep on getting. This kind of characteristics we will get. So this is your non-ideal case, but as of now we have drawn the ideal case. So if you are getting this doubt, then first thing is that very good doubt it is, and second thing is that we are going to discuss this particular doubt, and there I will take up all these doubts. Okay, so some very deep thing we have discussed there. I hope this deep thing is not reflecting you. Okay, like if we discuss too much, what will happen is that people will not be studying. If I just teach on the surface level by the equations, okay, this is the equation, this is the graph, then a lot of people will be attracted. But if we go this much of deep, then I hope you are able to enjoy it. Okay, so complete characteristics I have explained. There is no theory for this. You should write down the theory on your own. Wherever you want to write down, here there is space, here there is space, here there is space. Try writing down the theory, like VC was 0, then what was the scenario? This was forward biased, both were forward biased, that means there was very less current, then this became reverse bias. So now we are getting a constant current, but in non-ideal case, this current may be changing, right? This current will be depending because of this reverse bias. In this reverse bias, since this is more doped, that means most of the depletion region is towards this collector only, not in the base region. So since most of the depletion width is in the collector only, so here in the base, recombination is not changing, right? Like this is very important, that IB should not change with respect to this bias. This is very important. So if IB is changing, then IC will also change, right? So here another thing you can say, that if we are going upward, in this manner, so what is happening? VEB is increasing. VEB is increasing, along with that IC also increases, you can see. Along with that IB also increases. Are you able to understand this point? What I am saying, if I increase this bias, that means more holes will go here. If more holes will go here, that means more recombination will take place. More recombination will take place, that means more IB would be there. And if more holes are there, that means more holes will be attracted here as well. So more IC would also be there. So if you increase this VEB, IE will increase, IB will increase, and IC will increase. All will increase together. And this is very important. Like it should not happen that, sir, IB is increasing, IC is decreasing. Where it was happening? It was happening in your saturation region, that your IB was increasing, IC is decreasing. That I don't want. What I want, this is very, very important for me. IC equals to beta IB. And in a lot of textbooks, you would find that BJT is a current controlled current source, which is a baseless statement actually. Because of this IC equals to beta IB, it is known as, it is current controlled current amplifier, or whatever the statement that they write. So these statements are wrong. That's why I never write down these statements. Okay, current controlled current source, current controlled current amplifier, voltage current controlled current amplifier. Basically, I can make BJT work as anything. Here deeply, if you see, what you will call it? The IC current is depending on this VEB. IC current is depending on this VEB. So I can say that my current is controlled by this voltage. So why I cannot say current controlled voltage amplifier? Why I cannot say that? Why I need to say that current controlled current amplifier? Just because IC equals to beta IB. IB itself is a function of VCB, no? IB itself is a function of VEB, no? So like this is simply a baseless statement, no? That BJT is a current controlled current amplifier. Nothing like that. It is not a current control source. It can be a voltage controlled amplifier as well. So these baseless statements I never discuss. Like if you have studied somewhere, then ignore those statements. Okay. In analog electronics, I will, like what we will do, we will make all kind of amplifier: voltage controlled voltage amplifier, current controlled voltage amplifier, current controlled current amplifier, voltage controlled current amplifier. So from one device, or you can say from one device only, I would say, whether it is MOSFET or BJT, you can make any kind of amplifier. So saying that it is current controlled or current voltage controlled, that doesn't make any sense. Is that clear? Okay. It depends on the circuitry, how you are using it. Based on that particular circuitry, you can say that it is controlled by current, it is controlled by voltage. But just looking at a device, you can never say it is current controlled or voltage controlled. So what I was saying, that this IB is important for us, right? More and more VB, more and more holes will get into action, more and more recombination will be there, more and more holes means more and more holes will be swept here as well. So more IC, more IB, and more IE. So as you are going upward, VB is surely increasing, along with that IC is also increasing, IB is also increasing, and surely then IE will also increase. And there has to be linear relation between all of them. What is that? IC equals to beta IB and IC equals to alpha IE. So this relation has to be there. This is the relation that I wanted from the starting of the chapter. Is that clear? All good? All fine? So characteristics of BJT we have seen. Spent a lot of time here. Now basic question I will answer, like why collector width is the largest, right? Like why is it called BJT? So all these answer we will see. but before that I need to take a break. So I will take a break and come back. You can simply revise these characteristics. Okay, so let me take a break and then I will come back. Yeah, welcome back. So why collector width is largest? So why do we keep collector as a largest? So look, when you design a BJT, you design it in a manner that I will be operating it in active region. Basically, BJT was not designed to work in saturation or cutoff. I told you saturation and cutoff we can achieve using PN junction as well. So when I designed BJT, I designed it to work in active region. So by default, when I am designing, when I am doping P and P, here I will dope P plus plus, here I will dope N plus, and here I will dope P. So when I am doping, I know that this particular junction, collector junction, will be reverse biased. So when I explain this particular scenario, your doubt should not be there, sir, what if it was forward biased? No. When I am designing BJT, at that time, in my mind, it is going that my collector junction is going to be reverse bias and this is my forward bias only. So biasing is already going into my mind. In that scenario, I am designing my bipolar junction transistor. So let's just see what will happen if this is forward bias and this is reverse bias. So this particular junction is forward biased, and you know that in forward bias there will be less resistance, right? So let me show the less resistance by this. And this particular junction is reverse bias, this particular junction is reverse bias, and you know that in reverse bias there will be more resistance. Say yes or no? And here we are applying voltages. This voltage we are applying. So rough diagram I am making, okay? It's not that, sir, you can replace it with resistor. Just to explain you something, I am making these diagrams. Now what is the current that will flow from here, from this emitter node? IE current would flow. And here what current would flow? IC current would flow. This I am calling as R1, this I am calling as R2, or let's call it RE, emitter junction, and let's call it RC. So you know that at collector junction, the resistance would be much larger than emitter junction resistance. So what will be the power at the emitter junction? Power dissipated. That would be, sir, IE square RE. And what will be the power dissipated at the collector junction? So that would be IC square RC. Now what do you know? You know one thing, that IE and IC are same. IE and IC are same. IE and IC are nearly same. IC is nearly equals to IE. But this guy is much larger. RC is much larger. That means your power dissipated at collector junction would be much larger than the emitter junction. Power dissipation at the collector junction would be much larger than the power dissipation at the emitter junction. Why is that so? Because here the resistance is very large. Now, do you know one thing, like let's just say you are having some pot. This is your glass. This is your glass 1 and this is your glass 2. Both are having the same volume. Now I am putting some hot water in this one. I am putting some hot water in this one, and in this one as well I am putting some hot water. So in which pot water will be cooled down first? In which pot hot water will be cooled down first? In this one or in this one? The one which is having more area. That means more surface area. That means cooling will be faster, no? If my surface area is more, cooling will be faster. So if this surface area is more, cooling will be faster. So here as well the same scenario would happen. There is more power dissipation. More power dissipation means more heat. Heat at collector. Heat at collector would be much higher. And if heat at collector region, at a collector junction I should say, if that is much higher, so to compensate that particular heat, what you need to do? You need to keep the surface area larger, or you can say, I should not say surface area, you should keep the width larger. By this scenario you will be able to understand, right? Because if you put something which is generating heat in a less surface area versus if you put it in larger surface area, in larger surface area it will be cooling down easily. So I need to, whatever the power that has been generated, I want that because of that power some heat will also be generated, and I want that heat to be cooled down fastly. That's why the surface area of collector junction would be more than the emitter, like more than the emitter and surely more than the base as well. So did you understand this part, that why the surface area, I should not say surface area, why the width of a collector region is more than the width of emitter region. So this has been written here. The collector width is largest so that it can handle maximum amount of power, heat and voltage. A wider collector region allows the collector based depletion region to expand safely under reverse bias. Yeah, this is one more thing. Like if this was not much larger, if this particular width was not much larger, then like it might happen that this will be completely depleted of charge carrier. Basically, you are doing a reverse bias here. If you are doing a reverse bias, then depletion region will be extended. If you keep on increasing this reverse bias, depletion region will be extended. So it might happen that if it is not very large, then it might happen that your collector junction will be completely depleted of charge carriers. And if it is completely depleted of charge carriers, then current will not flow. So that is also one of the reason. Along with that, other reason was to compensate for the heat that is generated. Okay. So a collector width is made larger so that it can handle the maximum power, maximum amount of power, heat and voltage. Along with that, a larger collector region allows the collector base depletion region to expand safely under the reverse bias, and it spreads the generated heat over a larger volume. Like whatever the heat that has been generated, it will be spread over the larger volume. Like if this was having lesser volume, then heat will be in this much of amount only. But if it is having more volume, then heat will be separated in this manner, right? So your device will not burn out. That's the thing. Your device will not burn out. So this has been written. This prevents premature breakdown. Here breakdown doesn't mean larger current. Breakdown means device breakdown. When I am writing down breakdown here, I am talking about device breakdown. Device breakdown means device has burned out. Okay. So breakdown is not that particular breakdown which we studied in PN junction. Okay. In PN junction, whatever the breakdown we studied, that was larger current was flowing. So that breakdown also we will see here. But as of now, the breakdown means here is device breakdown and allows the transistor to carry large amount of current without any damage. Okay. So without any damage. So just to prevent your BJT being damaged, you are making collector region higher. You are making collector width higher so that the power will be dissipated across the more volume, not across the lesser volume. So if it is dissipated across the more volume, then your BJT will not burn out. Okay. Now why it is called bipolar junction transistor? So here what you can see, your power is being transferred from low resistance to high resistance. The word is transistor. Transistor. Transistor is made from transfer plus resistor. Okay. So transfer and for and RES is gone. Transfer resistor. So you are transferring your power, or you can say you're transferring any electrical signal. It could be IE, or you can call it power, whatever you want to call it. You are transferring any electrical signal from lower resistance to higher resistance. That's why it is known as transfer resistor or transistor. Basically, here what was the power I was getting? This much. At the output, how much power I am getting? Let's just say if this is my input side and this is my output side. So at the input I was getting this much of power, at the output I am getting this much of power. So at the output I am getting more power. Right? So that's why we are calling it transistor. All these names are given with respect to active region only. So whatever the analysis we do, we will consider that we are designing our BJT to operate it in active region. So transfer resistor, transfer plus resistor, that is known as transistor. And why it is called bipolar, that I have already told, because electrons and holes both are taking part in carrying the current. Why transistor? Because it transfers the electrical signal from low resistance input to high resistance output, ensuring power amplification. That's why it is known as transistor. Now there is one more phenomena that is known as thermal runaway. What is this thermal runaway? So let's just say you are designing some chip. This is your integrated circuit, or this is your chip. In this chip, somewhere you have used this NPN transistor, BJT you have used. Somewhere this has been used. Now somehow the temperature of this chip got increased. Like some other IC got some temperature, like some other IC started burning out. So somehow the temperature of this chip got increased. So somehow the temperature has increased. Now you know one thing, that if temperature increases, then Ni also increases. Ni square also increases, or Ni also increases, right? Because Ni is proportional to temperature. I told you Ni and temperature are inseparable brothers, right? Now what is your I naught? I naught is AQ dP Pn naught. So Pn naught is nothing but Ni square by Nd. So you also know that I naught is simply proportional to reverse saturation current. I'm talking about reverse saturation current, that is proportional to Ni square. So if temperature increases, then reverse saturation current increases. If your reverse saturation current increases, you know that IC is nothing but I naught e to the power forward bias by Vt minus 1. So if your Ni square increases, then I naught increases, then IC will increase. If IC increases, then this power dissipation would increase. If this power dissipation increases, then heat would decrease. Heat would increase. And if heat increases, then temperature would increase. More temperature, then more I naught would increase. IC would increase. Power dissipation would increase. Heat would increase. Again, temperature would increase. So this cycle will keep on going, and eventually your NPN transistor or PNP transistor may burn out because of the continuous increase in the temperature. Continuously temperature is increasing. Because of the increase in temperature, I naught increases, IC increases, power dissipated at the collector region, that is increasing. Because of that, heat is more. Heat means more temperature. In that manner, your BJT may burn out. But we will keep our collector region so large, that this heat dissipated is actually very less. Whatever the heat that is being dissipated, that is actually very less. So if very less heat is being dissipated, then very less temperature will increase. Okay, so this is also one of the criteria. In one liner, if you need to say that why collector region is largest, to avoid thermal runaway. That's it. In one liner, if you want to tell the line, that would be to avoid thermal runaway. That's why we keep our collector region or collector width largest. Then they will ask you what is thermal runaway. Then this is how you can explain. You can make this diagram as well. Okay. Let's just remove it. So somehow if temperature increases, then heat would increase. This is how the heat would increase. Because of the heat, again temperature would increase and your device may burn out. We will keep the collector region larger so that the heat is dissipated over a larger volume. If heat is dissipated over a larger volume, then the dissipated heat per unit volume will be less. So temperature will not be increasing. The temperature of my device will not be increasing in a larger manner. If it is not increasing in larger manner, then we will not go into thermal runaway. You cannot break this loop. There is no chance that you will be breaking this loop. But what you can do is that you can make the effect of this guy very less. If you are making the effect of this guy very less, then this effect will also be very less. If this effect is less, then this is less, this is less, this is less, then again this is less. So loop cannot be broken, but the effect of one parameter can be taken down. You cannot take down the current, right? Taking down the current is not a good way because we want amplification. And if current is more, then this will be more, this will be more. So, but you can take out the heat. You can reduce the amount of heat that is being generated. I hope that is clear. So all these are like one-liner question in gate examination. How they can be asked in statement? Which of the following statements are true? 4 statements they would write down, and this is how they can ask. Otherwise, in the interviews, they are very famous question. These questions are very, very famous. Okay, in the interviews. Now we are going to see the non-ideal characteristics. Have we seen this characteristics? IC versus VEC. Right. Now, what do you think? What all kind of non-idealities we can have? One is breakdown. Basically, it is like a reverse bias characteristic only. No, in diode, it is like a reverse bias characteristic only. And when you increase the reverse bias, here if I increase the reverse bias too much, then what will happen? Larger current can flow, and that we were calling as breakdown. Jenner breakdown was there, or avalanche breakdown was there. So breakdown may occur at a very large reverse bias. So similar scenario can happen here as well. So we will talk about the breakdown. Along with that, one more scenario is there that we discussed in detail, that now we are going to discuss in detail, but in brief manner I have already told. What I say, that till this point we were in saturation region, but after that we will come in active region. So in this active region, you said that, sir, your IC will not be changing with respect to increase in VC, but actually there would be some effect of VC for sure. How that effect would be there? So let's check that out. So ideal characteristics we have already made. Let's not read this theory. I will not let you see it. Okay. So don't read this theory. Okay. So ideal characteristics we have already seen. This was our ideal characteristics. This was our ideal characteristics. But practical characteristics would be somewhat like this, that there would be some slope for sure. This I am calling as VBE. Let's just say VBE is 2 volt. And here I am saying VBE is 2 volt only. So this is your ideal and this is your practical or non-ideal, you can say. Well and good. So let's see what really happens. So you know that like initially we will be in saturation region. So till this point I don't need to discuss again, right? Until you apply VEC equals to 2 volt, this will be forward bias, this will also be forward bias, very less amount of current would flow. Now when I increase VEC further, then what will happen? This guy will come into reverse bias and this is already forward biased, which I don't care about it. Okay. Now if you keep on increasing the reverse bias, then what will happen? The depletion region will keep on increasing. The depletion region, here it is less extended, here it is more extended. But there would surely be some increase in the depletion region. And here there was very less depletion width, very less depletion width was there, very less. Now this phenomena is known as base width modulation or Early effect. Early is the name of a physicist. The guy who found out about base width modulation, the name of that guy was Early. So there is no meaning of Early here, okay? Early is the name of some guy. So better we call it base width modulation. So initially this was my base width. This is our neutral region base width. As I increase the reverse bias, what will happen? The neutral region base width will go down. The neutral region base width will go down. If your neutral region base width is going down, then let me know what will happen inside the base. Recombination would be lesser. Why did you keep this width lesser? So that you can reduce the number of recombination. If 5 holes are coming from here, you want that all 5 holes should be reaching here. But there is some width of this base region. Because of that, out of 5, 1 hole was being recombined and 4 were reaching here. But as you increase the reverse bias, the depletion width is becoming narrower. Sorry, not depletion width, base width is becoming narrower, depletion width is being extended. Depletion width is being extended and this base width is becoming narrower. If narrower base width means less recombination would be there, and less recombination means more collector current. And this I am doing when this is fixed. I have fixed it. If it is fixed, then what you would expect? That sir, my IC current should be fixed only. This should also be fixed. If this is fixed, then sir, I would expect that this should also be fixed in a linear region. So what we are talking about? We are talking about active region, you can call it, or linear region, you can call it. So in active region, so previously I was expecting that if you change VEC after a certain voltage, because here we are getting into active region. So in this active region, sir, I expected that no matter whatever the VEC I increase, this current will not change, because this will directly depend on VEB. It will not depend on VEC now. This is what I expected in active region. But actually what is happening, if I am increasing this voltage, then reverse bias here is being increased. How it is increased, you already know. If you increase this voltage, reverse bias here will be increased. If reverse bias is being increased, then your base width is being modulated. What I am saying, your base width is being modulated. That means your base width is becoming very narrower. And if it is becoming narrower, that means there will be lesser recombination. If there is lesser recombination, then more and more holes will be reaching here. If more and more holes are reaching here, that means more and more collector current would be there. So what is happening? Lesser recombination, that means this IB current that you are having, this IB current is going down, IC current is increasing, but that is very minute amount. In very minute amount it is happening. So eventually your IC is actually becoming a function of VEC. But this is something that I did not want. I did not want IC to be a function of VEC, but actually it is becoming a function of VEC. Say yes or no? Okay, so that's why with the increase in VEC, somehow, like this is very minute amount actually. This amount is very minute. So with the increase in VEC, some IC current is increasing. Not in a larger amount, but in a lesser amount only. Why not in larger amount? Because our base is more doped. If base is more doped, that means the depletion region, whatever the extension in depletion region will happen, that will happen towards the collector region only, not in the base region. In the base region, what will happen? The depletion region will not be changing much. Like it might be changing for 0.001 micrometer. which is a very less change. That means whatever the base width previously I was having, even after increasing the VEC, the base width is not changing much. That means the recombination amount is not changing much. So if you are not doing anything with VEB, that means your IE is same. Nothing is happening with IE. If IE is not changing, and if you increase VEC, your base width is also not changing. That means amount of recombination is also same. That means IB is also same. So if IE is same, IB is same, IC has to remain same only. But if your base width is being modulated, then there is some problem. If base width is being modulated, then there is a problem. The problem is that this width is becoming lesser. That means amount of recombination is becoming lesser. If amount of recombination is becoming lesser, more and more holes are reaching here, collector current is increasing. Or what you can say, sir, VEB is fixed. That means this is also fixed. If VEB is fixed, that means, sir, this is also fixed. Sir, if this is fixed and you are saying that IB is decreasing, why IB is decreasing? Because lesser base width is there. If lesser base width is there, that means less recombination. That means this is decreasing. If this is decreasing, and you know that IE is equals to IC plus IB. So this is fixed, this guy is fixed, and you are saying that this is decreasing. So it has to increase only, no? So that it remains fixed. If it was 2 ampere, from 0.1 ampere it has become 0.05 ampere. That means the 0.05 ampere will be compensated by this guy. So this has to increase. So as you are changing VEC voltage, base width is being modulated. Because of that, IC is increasing. Very simple thing, and this is known as base width modulation. Okay, so theory has been written. Base width modulation occurs when the reverse bias across the collector base junction increases, causing the collector base depletion region to extend deeper into the base. As this depletion region widens, the neutral base width will become smaller. Neutral base width will become smaller. A narrower base means fewer carriers recombine in the base, so more of injected carriers will reach the collector, causing the collector current to increase even though the emitter base voltage is unchanged. Even though this voltage VEB is fixed or unchanged, you can say. This dependence of collector current on collector voltage is called base width modulation or early effect. So dependence of IC on collector voltage, or you can call it V, because we will take it as a reference. Emitter is reference, like emitter will be 0 voltage. So that's why here it is mentioned collector voltage, but actually it is VEC voltage. But V will be 0 only, no? So IC has become a function of collector voltage here. Okay. Now what happens if you keep on increasing this reverse bias? If you keep on increasing this reverse bias, then there will be one time, like at some reverse bias, what will happen? This base will be completely depleted of charge carriers. What I am saying, if you keep on increasing this reverse bias, then what will happen? Depletion width will keep on increasing. At some particular voltage, like this width will keep on increasing. After that, what will happen? This width will keep on increasing. In that manner, it will keep on increasing. At some voltage, what will happen is that this particular width will be, this guy will be reaching here. That means whole base will be depleted of charge carriers. At some reverse bias, whole base will be depleted of charge carriers. And this condition or this phenomena is known as punch through. What it is known as? Punch through. When your base is completely depleted of charge carriers, that phenomena, that condition is known as punch through. And the reverse bias voltage, and this reverse bias voltage, where it happens, that is known as punch through voltage. Okay. So as you keep on increasing the reverse bias across the collector junction, at some particular reverse bias, the base region becomes completely depleted of charge carriers. So the depletion region extends till the collector junction. So now there are no free charge carriers available in the base. Now what will happen is that whatever the holes that are injected here, they will feel a very high electric field and they will be very fastly swept away to the collector, and a large amount of current can flow, and because of that your device may get damaged. So this has been written in punch through. Simple theory it is, you will be able to understand every single line. If you are listening to me very carefully, every single line you will be able to understand. Punch through occurs when the reverse bias at the collector base junction becomes so large that the depletion region extends all the way through the base and reaches the emitter depletion region, right? Completely it is depleted. When this happens, the neutral base region disappears or becomes extremely thin. Okay. As a result, there is no recombination in the base region, there is no recombination, there is no controlled base region left to limit the current flow, and the carriers injected from the emitter are swept directly into the collector with almost no recombination. Whatever the holes came, all are swept away because there is no recombination that is happening. This causes a sudden and uncontrolled rise in collector current, often damaging the transistor. In simple term, punch through means the depletion region punches through the entire base. The depletion region punches through the entire base, destroying the normal transistor action. Is that understandable to you? So this is known as punch through voltage. Now just answer me one question. P N plus and P. This was P plus plus. If I make it lesser doped, let's just say if this was P plus and this is the scenario. So if I make it lesser doped, or in some other transistor, what I have done? Here I have made it more doped. So in which condition punch through will occur first? In this condition punch through will occur first, or in this condition punch through will occur first? Let's just say at 5 volt I am saying that in this condition at 5 volt punch through has occurred. So here you would require more than 5 volt or less than 5 volt? More than 5 volt. No, in this one we will require more than 5 volt. That means punch through will be occurring first here. Why in this one punch through will occur first? Because this is more doped, this is lesser doped, and depletion region will be extended towards the less doped region. So depletion region will be extended towards the less doped region. So here I will require lesser reverse bias to make it completely depleter of charge carriers, and that I don't want. I don't want it to be completely depleter of charge carriers. I want some base current as well, I want some collector current as well, I want some emitter current as well. Everything I want. I want my VEB to control my IE. If IE is there, some IB should also be there, and then some IC should also be there. This is something that I want. I don't want that IB should become 0. If IB is becoming 0, that means there is no recombination and reverse bias is making some impact. Like this particular reverse bias is making some impact on IC. So this is not my desired condition. This is not my desired condition. I don't want this particular condition. I want IC should be beta IB. This is something that I want. I want this particular operation. Right? So punch through is not a desired condition. For my amplifier purpose, when we study amplifier, you will realize that punch through is not a desired condition. Because in punch through, what is happening? Nearly zero recombination is taking place. Okay? And large amount of current would flow. Uncontrolled current can flow. Like you are not able to control the current. Only VEB is not controlling the voltage. Whatever the reverse, only VEB is not controlling the current. Whatever the reverse bias that you are applying, that is also controlling the current. And that I don't want. I want only VEB to control the current. I want only this guy to control this current. But this is coming into action. So to avoid base width modulation or to avoid punch through, we keep the base doping larger. This is the region, not the fabrication. Okay. So again, a very, very important point. I don't know why it is taught in wrong manner everywhere. So this has been written here. If we keep the doping concentration of base higher than that of the collector, then under reverse bias, most of the depletion width will be extended toward the collector side. If your base doping is more. The collector is long and lightly doped, so it can safely accommodate a large depletion region. Collector will not complain. Collector will say that I am already very long. So if you are extending depletion region in me, I am fine with that. I don't have any issue. Only a small portion of the depletion region enters into the base because the base is more heavily doped than the collector. As a result, the neutral base width does not change much, does not shrink much, which help us to avoid early effect and punch through condition. That's why the base is doped higher than the collector. So this is the exact region, not the fabrication. Okay, this is very surprising to me that teachers will act as if they are the god, and these god educators say that because of the fabrication, practically we say that base is more doped than a collector. Not practically, theoretically as well, base will be doped more than the collector. Okay, like in the first go, it may look like that, sir, base should be less doped because we want lesser recombination, right? In the first go, when I am designing, when I am getting the first idea of PNP, first idea was that I want to inject more and more holes into the collector. So at that first time, it might feel like that, sir, dope very less doping you should do in the N side, or very less doping you should do in the base, so that lesser and lesser holes get recombined. But as you move ahead in the chapter, you get to know that yes, this recombination is also very important, because if this recombination is not taking place, then my collector current is controlled by the reverse bias, and that I don't want. Okay, so this is how you should be studying the things. I hope it is clear. If someone asks you in a good ISC interview that why your base is doped higher than the collector, then you should be able to answer in this manner. Okay, not because of the fabrication. And these things are written in Niemann as well. It's not that like blindly I am making something in my head and I am teaching here. In Niemann, all these things are written. It is not written that because of the fabrication it is highly doped or lesser doped. Okay, so now everything is clear. Now every reasoning is clear. Why it is called as BJT? That is also clear. What about the width? Width of a collector is larger than the emitter than the base. This is also clear. What about the doping? Doping of emitter is largest than the base and then the collector. So all these scenarios are now clear to you. Every single thing you know and every proper reasoning you know now. Proper reasoning you can tell. Say yes or no. Along with that, there was one more point which was thermal runaway. So this also you can explain. Along with that, you can explain the characteristics as well. And yeah, when you increase this particular line backward, then it will meet somewhere here, right? So at the point when you increase this line and you pull it backward, at the point where this where this IC becomes 0, this is known as early voltage. So at early voltage, this IC would become 0. This was the line, like this was your non-ideal characteristics. This was your non-ideal characteristics, right? This was your non-ideal characteristics. This was your non-ideal characteristics. Now, if you draw this line backward, on the x-axis, it is cutting on VA. It is known as early voltage. Why this early voltage is important, you will understand in analog. Okay? Because it will result in some output resistance. That is VA upon IC. So all these things you will see in analog. Okay, so where this VA would be important, how we will change the collector current equation. Like collector current equation we used to write down in this manner, no? V by eta Vt minus 1. But eventually what will happen? 1 plus mod of Vc by Va. That would also come into action. So all these equation you will learn in analog. Don't worry about it. Okay. So yeah, this is known as early voltage. If you just extend this particular line backward on x-axis wherever it meets, that means when Vc is equals to minus Va, at that time your collector current would be 0. So this would be your equation, that whatever that we have studied plus Vc mod divided by Va. Okay. So when your Vc mod you put, like basically it is a reverse bias. Even if it is a reverse bias, then I will put the positive value. This is what I am saying. So when this mod of Vc is equals to minus Va, sir, what you are saying? How mod can be negative? Basically, I am saying that when you have applied the reverse bias equals to minus Va, at that time your collector current would be 0. Okay. So all these things will again come into analog. We will see it. But here I just need to explain the physics. So physics we have explained. How we will use it in circuitry, that you study in analog. So physics is completed here, right? This numerical we need to solve and this numerical we need to solve. And I would say it is important. I would say it is important. Can be coming in your examination, because from BJT, like this is the point from where I can frame some question. One was that current, right? We solved one numerical where we asked the value of emitter injection efficiency, base transport factor, alpha, beta, collector current, emitter current. One was that topic and other one is this topic. If I want to frame numerical problem, then only these are the topics. Theoretical problems can be framed. A lot of theoretical questions can be framed, right? But for numerical, this is important. Like you will be able to understand, I guess you will be able to solve this question. What they are saying, uniformly doped silicon BJT is there, bipolar junction transistor with the metallurgical base width is given. Base width is given. Okay. So although you know that, sir, base width is very less, but I will make it larger to explain this question. Okay. Just to explain this question, I am making it larger. So base width is 0.5 micrometer. This is your metallurgical base width, not the neutral agent base width. So metallurgical base width is 0.5 micrometer and the base doping is also given, that is 10 to the power 16. Collector doping is also given, which is 8.38 into 10 to the power 14 centimeter cube inverse. Assume complete ionization and epsilon R value is given. Find out the punch through voltage. Punch through voltage, what is punch through voltage? Punch through voltage is the reverse bias across a collector base junction, whatever the reverse bias that you apply. So let's remove this 0.5. I will write down inside. So now what I am going to do, I am going to apply a reverse bias here. No? Is it PNP or NPN? Nothing is given. So I will simply write down reverse bias here. Reverse bias. I am applying reverse bias. So whatever the reverse bias I apply here, so how much reverse bias I need to apply such that this base gets completely depleted of charge carriers? This is the question that they are asking. Dopings are given. This is the doping that has been given. This is the doping that has been given. What do you want? You want depletion width to be 0.5 microampere. Sorry, do you want depletion width to be 0.5 micrometer? No, I want depletion width in base side to be 0.5 microampere, not microampere, micrometer. Okay, what I want, let's just say my depletion width, whatever it is, I don't know, it would be xb plus some part would be there in the collector as well. Are you able to understand this point? Like some part of base will be depleted and some part of collector would also be depleted. So how much base will be depleted? So base will be depleted of total depletion width multiply with nc upon nc plus nb, right? Because in the inverse proportion depletion would be there, and you want that complete base should be depleted. What is given? Ignore space charge region of B junction. That means whatever the depletion region that is coming into action from here, that we need to ignore. So I don't need to consider emitter. Simply it is this kind of question we have already solved in PN junction only. So simply it is a PN junction question where they are asking that how much reverse bias I need to apply such that this gets completely depleted of charge carriers. This is the question. That's it. So this is my 0.5 microampere. Sorry, 0.5 micrometer. So xb equals to 0.5 micrometer. So what should be my total depletion width? That I can find out. Are you able to understand this point? So total depletion width should be from here, depletion width, if I find out, that would be nc plus nb upon nc. So this will be your total depletion width. And what will be the formula of this total depletion width? That would be under root 2 epsilon by q 1 upon nc plus 1 upon nb v built in plus v reverse bias. So this reverse bias we need to find out. V reverse bias we need to find out. I have the value of nc, I have the value of nb, I have the value of epsilon, I have the value of q. V built in I can find out. What will be my v built in? That would be, sir, 0.059 kt ln nc nb by ni square. So 8.38 into 10 to the power 30 divided by ni square. Ni value is given, yes, 10 to the power 10 it is given. So from here I can find out the built-in potential. Into 0.0259, so 0.651. सही तो किया ना यार कैलकुलेशन? 8.38 था, 20 था, ठीक है. So 0.6514 volt. I hope you are understanding this equation. I hope it is not very tough for you to understand, right? In the base region I want a 0.5 micrometer. So in the collector region as well there will be some depletion. Whatever that depletion is there, I don't know. I care about total depletion width. So what will be my total depletion width? Total depletion width will be simply xb plus xc. Now I know that xb ratio xc is nothing but nc ratio nb. So your xb would simply be total depletion width multiplied with nc upon nc plus nb. So that I have done. From here total depletion width would be xb into nc plus nb divided by nc. Now what is the value of xb? xb is 0.5 micrometer. Now what will be nc plus nb? If you add nc plus nb, which will be, that will be nearly equals to nb only. NC plus NB, nearly equals to NB only, right? Divided by NC is given, no? So 108.38. Let's put it 108.38 into 10 to the power 14, right? 100 into 10 to the power 14, 8.38 into 10 to the power 14. So 108.38 into 10 to the power 14. NB plus NC divided by NC. NC is 8.38 into 10 to the power 14. Okay, and then under root 2. Like, I hope you are not getting confused with this diagram. Don't get confused with this diagram. You might see that, sir, XB is greater than XC. No, you know that surely XC would be greater than XB. There is no doubt about it. It is just the diagram, right? XC would surely be greater than XB. No, because here doping is less. Less doping means more depletion width. So no doubt about it that XB would be greater than XB. XC would be greater than XB. Epsilon, what is the value of epsilon? 11.7. One by NC plus 1 by NB. You know that 1 by NB will be much lesser than 1 by NC. So only 1 by NC I will take. Basically, this I will ignore. Okay, only 1 by NC I will take. Approximate answer I can tell. 8.38 into 10 to the power 14. V built in plus VR. V built in is 0.65 plus VR. So there you go. This is the equation you need to solve now. Okay. So what we are getting? 108.38 divided by 8.38 into 0.5. 6.46 micrometer. Okay. Actually, I don't remember the answer of this one. Here answer also I did not write down. So I will have to solve it. So 10 to the power minus 28 would go here. What I can do, 10 to the power minus 5, that goes 10 to the power minus 9, 10 to the power minus 4 I can take outside. 10 to the power minus 4 I can take outside, right? So 6.46 only I can put here. Like basically this is something we were getting, right? Centimeter. And here also everything would come in centimeter only. So what I am doing is that this would become 10 to the power minus 5, 10 to the power minus 19, 10 to the power 14. So 10 to the power minus 5. Upside it would go, so it would become 10 to the power minus 9. So if I give 1 10 to the power here, 10 to the power minus 1 here, so 10 to the power minus 4 I can take outside, right? So what I can do is that this would become 0.2, 11.7 into 8.85, 1.6, 8.38, 0.65 plus VR, and then you take the under root, and outside I am getting 10 to the power minus 4, and this will get cancelled out. Okay, so whatever the answer I am getting, then I can do the square of it. Then 1.6 into 8.38 divided by 0.2 divided by 11.7 divided by 8.85 minus 0.65. 26.42 I am getting. इतना तो नहीं था यार. As far as I remember, it was 24 something. How I am getting 26? 8.38. No calculation error, right? 2 epsilon by EQ, 8.84 Q, 1 by NC, 1.38, 1 by NB I ignored. Everything is fine. 10 to the power minus 28, 10 to the power minus 5 minus 9, so 0.2, 10 to the power minus 4. So it is coming out to be 26.42. If you are getting some other answer, then you can check it. Okay, I am getting 26.42 volt, roughly around this voltage. Okay, so you can check it on your own. This is the answer that I am getting. Okay, so check it. I am putting check. As of now, during the calculation, this is the answer I am getting. But when I solved it, actually I have taken this question from Niemann only. So in Niemann, they asked you to find out the NC value. They have given the punch through voltage. They asked you to find out NC value. Then they took some approximation as well. So that was not a good question. So I reframed the question. There, as far as I remember, punch through was coming out to be nearly around 24 volt. It is coming out to be 26 here. So you need to check. Okay, might be some calculation error. You can check on your own. Concept is clear to you. Like in Niemann, what you would find, like a lot of people, what they would do, they would forget this built-in potential. Built-in potential we should not be forgetting, because built-in potential will also give some depletion width. No, reverse bias will also give, built-in potential will also give some depletion width. So let's try this one. N plus plus P plus N is there. Reverse bias you are applying. All the dopings mentioned. Punch through voltage is mentioned this time. You need to find out the metallurgical base width. So this base width you need to find out. What is the meaning of punch through? That at 4 volt completely it will be depleted of charge carriers, right? So this width I need to find out. So at 4 volt, what will be my depletion? My depletion would be WB multiply with NC upon NC plus NB. Oh, sorry. My WB would be this thing, right? WB would be W depletion into NC upon NC plus NB at punch through, right? At punch through. Why at punch through? Because at punch through it will be completely depleted of charge carriers, right? All good, understandable it is. Can I find out W depletion? Surely I can find out W depletion. But along with that, I would require the value of built-in potential as well. So first I will find out the built-in potential, 0.0259 kTln 5 into 10 power 10. Because here 5 into 10 power 15, 10 to the power 15, that would become 5 into 10 power 30 divided by Ni square, that would be 10 to the power 20. So what I am getting, 5 into 10 power 10. Okay. So 10 to the power 10 into 5 ln into 0.0259. So 0.638. Built-in is coming out to be 0.638 volt. So now what will be your W depletion? That would be under root 2 epsilon by Q. What is the value of epsilon? 11.7. 10 to the power minus 14 under root 2 epsilon by Q. 1 upon Na Nb. So 5 into 10 power 15 plus 1 by 10 to the power 15 into V built-in plus Vr. What is the value of Vr? Vr, that is 4 volt. Okay, so I can solve this one. What I would do, upper side it would become 1.2 divided by 10 to the power 15. So 10 to the power minus 14 will go out completely. So 1.2 would remain there. So 2 into 11.7 into 8.85 into 1.2 into 4.638 divided by 1.6, 26.83. 26.83। अरे भाई ये हो क्या रहा है यार, 26.83 इतना सेंटीमीटर थोड़ी ना आएगा, इतना तो नहीं हो सकता। दिस मस्ट सेंटीमीटर, दिस इज कमिंग इन सेंटीमीटर। Again we have to do the calculation, 2 into 11.7 into 8.85, 2 epsilon by q divided by 1.6 into 1.2 into 4.638, then oh, 10 to the power minus 5 is also outside. No, this is 10 to the power minus 4. 10 to the power minus 5 will also come outside. This much centimeter we are getting. So basically it would be 2.683 micrometer. This is the W depletion we are getting. So what do you think, what will be your WB? So WB would be 2.683 multiply with NC, which is 10 to the power 15, divided by NC plus NB. So 10 to the power 15 plus 5 into 10 to the power 15. Right? So it is basically 1 by 6. This is 5 times of this one. So 1 by 6 times 2.683 divided by 2.683 divided by 6, 0.447. So this is the answer we are getting. Okay, this is the depletion width. Actually it is very less, you will not keep this much of depletion width. So this is the answer we are getting. Okay, I hope it is clear to you that my base should be completely depleted of charge carriers. So if I want my base to be completely depleted of charge carriers, that means depletion width should be extended till base, right? So what depletion width I will get? I am assuming it is W depletion. So W depletion would be WB would be W depletion into NC by NC plus NB. W depletion I can find out under root 2 epsilon by Q, 1 upon NA, sorry 1 upon NC plus 1 upon NB into the total for reverse bias plus the built-in potential, okay, which is 0.638. So that I apply here, and from here I got to know that my depletion width is 2.683 micrometer. Out of this, how much portion will be in the base side? So in the base side only this much portion would be there, rest of the portion would be there in the collector side. So they are saying that at 4 volt punch through is occurring. That means at 4 volt complete base is being depleted of charge carriers. So base width would have been 0.447 micrometer. Okay, that's it. So more known idealities are there. Next we need to see breakdown. Along with that, 2 or 3 more known idealities are there. So we will see that, but I need to change the slide because pages have ended. So I will change the slide, then I will come back and we will see more known idealities. Okay, breakdown we will see. Yeah, thank you. I will change the slide and then I will come back. You can also take some break and drink some water. Yeah, welcome back. So now we need to discuss the known idealities. So second known ideality we are going to discuss, that is breakdown. So in the same way, we have studied breakdown in PN junction as well. No? So whatever that used to happen in PN junction, the same scenario will happen here. What we studied in PN junction, let's just recall it. So this was our PN junction. In this PN junction, we had a depletion region. When we apply the reverse bias, what will happen? This electric field will become very strong, right? This electric field will become very strong. This is I can call PN. So this will be your electric field. This will become very strong. Since this has become very strong, what will happen? We will talk about avalanche breakdown here. Okay, what we will talk about? Avalanche breakdown. We will not talk about Jenner breakdown here. We will talk about avalanche breakdown. So since this electric field has become very strong, what will happen? Inside the depletion region, whatever the electron were present, they will get enough kinetic energy, and whatever the bound electrons were there, this electron would get enough kinetic energy and these bound electrons will knock off these electrons. If these bound electrons are knocking off these electrons, then what will happen? Electron hole pair will be generated. Now this electron and this electron will knock off other bound electrons as well. Then more electron hole pair will be generated. More electron hole pair will be generated. In that manner, a lot of electron hole pairs will be generated and those electron hole pair inside the depletion region, a lot of excess electron hole pairs you will be getting, and those electron hole pairs will be swept away by this electric field and a large amount of current would flow, and this kind of characteristics we got. So ditto same scenario will happen here. Ditto same scenario. It will happen in reverse bias. And which junction will be reverse bias? Surely the collector junction will be reverse bias. So if your collector junction is reverse bias, then the breakdown may occur. Again, in very brief manner, I will repeat what was the breakdown. Inside the depletion region, strong electric field will give kinetic energy to the electrons. These electrons will knock off other electrons and will generate electron hole pairs. Now these two electrons will knock off other two electrons which are bound, then it will generate more electron hole pairs. Then 4 electrons will be there. From 4 we will get 8 electrons. From 8 electrons we will get 16 electrons and 16 holes as well. So electron hole pair will be, a lot of electron hole pair will be generated. Those electron hole pair will be swept away or they will be drifted by this particular electric field and we will get a very large current. This was the scenario of our avalanche breakdown. The same scenario would happen here. We will talk about two cases. First one we will talk about emitter open and second one we will talk about base open. So first let's talk about emitter being open circuited. So this is our collector junction which is reverse biased. This is our collector junction which is reverse biased. Okay. So there is this electric field present. This electric field is present. Now you are applying an external bias. So this built-in electric field is also there and external electric field is also there. So electric field will increase. Ditto same scenario would happen. If this electric field is increasing, then what will happen? Electron hole pair will be generated. How they will be generated? Electron will get enough energy. They will knock out other bound electrons. Hole will be generated. Then more electrons will be there. These two electrons will knock out other bound electrons. Electron hole pair will be generated. A lot of electron hole pair will be there and the large current would flow. So when there was no breakdown, then how much current was flowing? Do you remember this current? ICBO. Current between collector to base when emitter is open circuited. The current between collector and base when emitter is open circuited. This was your ICBO current that was flowing. But ICBO current would flow for some time only. After that, breakdown would occur. Okay. Similar scenario is there in this particular region as well. What will happen here? I told you about this particular bias. This particular, whatever the bias that you have applied, that will be dropped across P++, N+, and P. That means this will be your forward bias. This will be your reverse bias. But I told you this will be low forward bias. What is the meaning of low forward bias? That only very less amount of holes will be going from here to here. Right? But here there is very high reverse bias. Because of this high reverse bias, what will happen? The same scenario would happen. Again, electric field will be built up. Stronger electric field will be there. Stronger electric field will be there. Then what will happen? They will be sweeping electron and holes and a larger current would flow. But the question would be, only one kind of question can be asked. The question would be that which breakdown voltage will be low. That means where breakdown would be occurring first, in this condition or in this condition. Let's just say I am saying that at 5 volt breakdown is occurring and other breakdown is occurring for 6 volt. So where we will require 6 volt and where we will require 5 volt. That means in which condition breakdown would occur first, that we need to see. Here there is only one scenario. This is your simple PN junction, right? Simple PN junction, whatever that used to happen when emitter is open. But this is not simple. This is somewhat complex because here low forward bias is present. Reverse bias is also there. Low forward bias is also present. Along with that, there is another scenario. So look at this scenario with full concentration. Otherwise, you will simply be mugging up the final answer. But you don't need to mug up the final answer. You will look at all the explanation that I am giving with full patience. Okay. So under breakdown, what was happening? Electron hole pairs were generated. This was the direction of electric field. Now what this electric field will do? What this electric field will do? This electric field will sweep minority carriers on the P side towards this direction and minority holes in the N side in this direction. Because of that, the current would flow. Now this stronger electric field is there, no? And a lot of electron hole pairs are generated. So all the electrons will be swept towards base and all the holes will be swept towards collector. Do you agree to this point? So at the depletion region in the base, a lot of electrons will be present. No? Why a lot of electrons would come into action? Like let's just say in this n plus region, previously 10 electrons are present at equilibrium. Now because of this bias, since you have increased this bias, since you have applied a very high reverse bias, then what really happened? A lot of electron hole pairs were generated here. All the electrons got the force towards the base, all the holes got the force towards the collector. So now this base region has become more negative. Say yes or no? This n plus region has become more negative. This P is at the same potential only. Initially I said that this is low forward bias, but because of this breakdown, this has become a bit stronger forward bias, a bit stronger forward bias, I would say. A bit stronger forward bias. Previously I said that here 5 volt will be dropped and here 4.99 volt will be dropped. That means I am having a forward bias of 0.01 volt, which is not very large. And in this case I said that under when there is no breakdown, what kind of current would flow? ICEO, collector to emitter current, when base is open circuited. This current would flow, right? We were having very low forward bias. Also I said that ICEO would be more than ICBO. Why it is more? Because some holes will be coming here as well. But now what is happening? This forward bias has become stronger. If this forward bias has become stronger, that means more and more holes will be diffused here. So here more and more holes will be coming into action. And since there is a very strong electric field present here, very strong electric field, this very strong electric field, what it will do? It will sweep up these holes. So in this particular scenario, two things are happening. One is this internal electric field plus built-in electric field plus external electric field. What they were doing? Creating electron hole pairs, right? Because of that, large current was flowing. Along with that, this scenario happened that N plus became more negative. Emitter junction became more forward bias. More forward bias means more holes will be diffusing towards the N plus side, because forward bias means holes will be injected from P plus to N plus. Just as these holes got into this N plus region, already there was a very strong electric field. This electric field, what it did? It drifted those holes. And because of that, the current became very larger. Is that clear to you or not? So what do you think, who will require? And here what is happening? Here also the same scenario would happen. You can say that, sir, here negative, 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 these will come into action. But at the emitter there is no forward bias. Then what will happen? Whatever this extra negative charge came into action, that will be flowing through the base. Whatever this extra charge came into action, everything would be flowing through the base, and this ICBO current would flow, although at the breakdown more current would flow. So here this scenario did not take place. Are you able to understand this point? So in this particular case, when my base is open circuited, even if I apply low forward, even if I apply low voltage here, let's just say I applied 3 volt here only. So if I apply 3 volt here, let's just say in this particular region 2.99 volt was reaching. Now 2.99 volt would be there. Along with this 2.99 volt, what it will do? It will create some extra forward bias as well. And because of this extra forward bias, what will happen? The current would start flowing in larger manner at earlier voltage only. Basically, if I need here 3 volt, then here I would require 5 volt. Are you able to understand this point? Why I require 5 volt here? Because here whatever the amount of current that is flowing, if I want to flow the same amount of current here, then I would have to apply more reverse bias. But here I would have to apply lesser reverse bias. Is that clear? Why the current is large? This, what I have seen is that people relate with ICEO and ICBO. What they say? That ICEO is larger than ICBO. That's why here breakdown is occurring in a faster manner. No, this is not the reason. Because they are already very low current. No, so you cannot compare. We need to talk about the larger current. So here whichever the larger current that is flowing, and here whichever the larger current that is flowing. So in this scenario, larger current is like basically here 30 milliampere is the larger current. So here larger current will be 20 milliampere only. Are you able to understand this point? What I am saying? Here more current would flow, no, in this scenario, because here two things are there. One is breakdown, other one is sweeping these holes, because forward bias has increased. You are not going to find out these explanation in the books as well. They will simply write down the formula. Okay, can you believe that? And if someone tries to explain intuitively, then they will give like these senseless region, ICO, ICBO. You have to watch at least 4 to 5 NPTEL lecture, then you will understand these kind of depth thing. Okay, some teacher would be teaching some other thing, like some NPTEL professor would be teaching some other thing, some NPTEL professor would be teaching some other thing. So when you compile all of them, then this kind of content comes up. So I hope you are able to appreciate. And if you are not putting your full concentration, then you will not be able to understand. Eventually you will have to remember. What you will remember, that in open base, say in the case of open base, the breakdown voltage will be lower than the case of a open emitter. Why breakdown voltage is lower? Because breakdown would occur at the lower potential. And you will say that the region is this current, but this current is not the region. Who is the actual region behind this lower breakdown voltage? The actual region is that even if you apply low voltage, this will get good enough reverse bias, but along with that, this guy would become more forward bias. Because of that, more and more holes will come into action in the base region, and those more holes will be swept away by this particular electric field, and a larger current would flow at a lower potential only. But here I will have to apply larger potential. I hope it is clear. All the theory is written in a absolutely great manner. So we will read out the theory. So this we already know. But breakdown voltage in this case would occur faster than this case. So all the theory is written. We will read out the theory, and first we will draw the graph as well. So IC versus VEC graph we are drawing. That means we are drawing the graph for open base. And here we are drawing the graph for open emitter. Okay. So let's draw the graph. What do you think? What kind of graph we will be getting? Here if I draw the graph, then sir, this kind of graph you get, and this is your breakdown voltage. So breakdown voltage between collector base. What is this current? This current is ICBO. Here when the breakdown would occur at lower potential only. It can occur at 3 volt only. Why it can occur at 3 volt only? Because there is stronger forward bias as well. The stronger forward bias is because of this stronger forward bias, a lot of holes are coming into base, and these holes are being swept away by this electric field. That means at lower voltage only you will get a higher current. Along with that, this ICEO is higher than the ICBO. That means here the graph would go somewhat like this. So here I have made this much of a width, right? This much of width was ICBO, but here I have made the graph like this. Along with that, one more correction I need to do. The breakdown would occur here. The breakdown would occur, right? So breakdown would occur at a lower potential only. Yeah, this looks fine. Okay, so what you can see, this is lesser than. So in the case of open base, the breakdown would occur at lower potential than the case of open emitter. This question can be asked. This is the only question that can be asked from this particular topic. Like theoretical question can be framed, numerical question cannot be framed in this particular topic. So theory is completely written. Also I have written that breakdown occurs at a lower voltage in open base condition. Don't mug up this CEO, CBO. So if you mug up these kind of things, then in the examination you will be getting confused. It was open emitter, open base, nothing. Open base. What is the scenario? Open base. Open base means forward bias will be increased here. That means low voltage I need to apply. So breakdown would occur at a lower voltage in open base condition. That's it. In open emitter case, what will happen? Whatever the negative charge that is coming here, all will be swept in the base current only. All these excess charge will be swept in the base current only. So here this forward bias will not come into action, but in this scenario forward bias will come into action. Because of that, a lot of holes will be swept because of this electric field, right? So in the open base condition, the collector junction of the PNP transistor is reverse biased, and the avalanche multiplication creates some extra electron hole pairs. These electrons move towards the base region, but because the base terminal is floating, open base we are explaining, yeah, because the base terminal is floating, these electrons cannot escape and begin to accumulate in the base. What does that mean? That means here, whatever the excess electrons were there, they can escape through this particular path, but here they cannot escape through any path because base is open, no? So they will start accumulating in this n plus region. They will start accumulating here because there is no path. So they will start accumulating here, right? So in the base region, they will start accumulating. So this is what they have explained. These electrons cannot escape and begin to accumulate in the base. This accumulation makes the base region internally more negative, which effectively forward bias the, right? Internally it has become more negative. Because of that, the emitter junction has become forward biased, right? Once the base emitter junction becomes internally forward biased, the emitter begins to inject additional holes into the base. Now these additional holes, these injected hole further strengthen the avalanche process. That means initially whatever the electron hole pairs were there in this depletion region, now more holes have come into action. That means more charge carriers have come into action. That means more current would flow. So at lower voltage only the current would start flowing. So this is what has been written. The internal feedback makes the transistor break down at much lower voltage in the open base condition. What about the open emitter condition? In open emitter condition, avalanche again generates electron hole pairs at the collector base junction. Electron move towards the base, but the base terminal is now externally connected. Okay, the same process is going on. Electron will move here, but now they are externally connected. So these electrons will be swept away by this battery. Externally connected. So these electrons are easily removed from the base region. So it will not happen that base is becoming electrically negative. No, base is not becoming electrically negative. Whatever the excess electron came, they are swept away by the battery. Since the electron does not accumulate, since the electrons do not accumulate, the base does not develop any internal negative potential needed to forward bias the base emitter junction. Understood? Because the base emitter junction does not become internally forward biased, the emitter does not inject extra holes. Thus, the avalanche remains weaker and the junction can withstand a higher reverse voltage before the breakdown. So here I need to apply the higher reverse bias voltage to get the breakdown, just because holes are not coming here. This process is not happening. But here this process was happening. Is that clear? In which condition breakdown would occur first? You can read the theory on your own. Breakdown would occur first in the open base condition. Why is that so? Because the reason is that avalanche generated electrons get trapped inside the base, forward bias the base emitter junction, causing extra holes injected from the emitter and greatly boosting the avalanche effect. In the open emitter case, these electrons are drained away through the base terminal, preventing feedback and giving a higher breakdown voltage. Right? So all this completely understood. So no formula, nothing. Like here, needless formulas are derived. In the examination, they will never ask question from needless formula. They will ask these kind of intuitive question. Okay. So if you have read some formula just to prove that BVCO is less than BVCBO, then don't remember those formula. Okay. Those formula will not be helpful in the final examination. In some test series, they may frame some question, but in the final examination, they will not be helpful. In the final examination, only this kind of question can come up. That's it. Right? Now let's see some important plots. Ideal plot we will see versus non-ideal plot we will see. So non-idealities are only we are studying, right? What was your IC? IC was I naught e to the power VB by VT minus 1. So what do you think what will be the ideal plot? IC versus VEB. Okay, here VB I am writing, so it would be VEB. So what will be your IC versus VEB plot? Sir, simply exponential. Like initially it will not be exponential, but eventually it will become exponential. This is like a forward bias plot only, no? This is like a forward bias plot. And if I draw it on a log scale, then what kind of plot I will get? This kind of plot I will get. But this is your ideal plot. Do you remember the relation between this IC and VEB? Yes, sir. IC was I naught e to the power VB by VT minus 1. This relation I already know, sir. If I draw it on the normal scale, then this is the graph I will get. If I draw it on the log scale, then sir, this exponential would become linear only. So this linear graph I will get on linear scale. But what is this? This is your ideal plot. Have we seen the non-ideal plot for forward bias? This is like a forward bias equation only, no? So have we seen the non-ideal plot for forward bias? Yes, sir. initially it would go like this, but at the high level injection the graph would become somewhat like this. Have we seen it? Absolutely. So do I need to tell you the reasoning? Absolutely not, sir. So this is your high level injection. In PN junction forward bias, we have seen it in a great manner. So I don't think here you should be getting any confusion. High level injection is there, because of that IC was supposed to increase, but it is not increasing the way it was increasing previously. So previously it was increasing with e to the power v by vt, now it will increase with e to the power 2 by vt. That's why the factor neta came into action. In great detail we have discussed it. So here I am not going to discuss. Directly I am going to make these diagrams, and these diagrams are very important because they are given in Niemann and till this date they are not asked. Okay, this question have not been asked and it is given in the book of Niemann. Another plot we will see, beta versus IC plot. Beta versus IC plot. So what is beta? So all these plots I will make. Okay, if you want to write down any theory, you can write down here. I will give you some space. There you can write down the theory. But eventually you need to remember the graph. In the examination, what they will do? They will simply make the graph and they will ask it whether this particular graph is correct or not. That's it. Basically, for a non-ideal PNP BJT, the graph between the collector current and the forward bias voltage have been shown. Which of the following graph are correct? This kind of question would come. Here also, what is beta? Beta is common emitter current gain. So common emitter current gain beta versus IC plot is given. Which plot is correct? These kind of questions will come. So let's get started. This diagram would be there. This diagram I will take as a reference. So if I increase my forward bias, if I increase my VEB, then what will happen? IE will increase. Along with that, IC would also increase. Right? Say yes or no. And along with that, IB would also increase. So eventually your beta increases only. Okay, like IC would increase exponentially, no? IC, expression of IC is this one. It would increase exponentially. So eventually, and IB would also increase, but not as much as IC. Like basically, if this is also increasing and this is also increasing, so what you would say, beta would increase or decrease? So then you will ask, sir, which guy is increasing more? So IC would increase exponentially, no? So if this guy is increasing exponentially, this is also increasing, but not in a very high manner. Okay, because IB value is already very low. So initially when IC increases, if your IC increases, beta would increase. If your IC increases, beta would increase initially. Okay, but after some time what will happen? Let's see that. If you have increased VB so high, VB so high means more and more holes will be injected here, more and more holes will be injected here, more and more holes will be injected here. If more and more holes will be injected here, that means this particular base will be filled with more and more holes. If base is filled with more and more holes, that means more and more electron supply will start. That means more and more base current will start. That means if VB is increased so much, then your IB will increase so much. But your IC will not increase so much. IC will be moderate only. Right? But because like this is the relation of IC versus VB, no? Are you able to understand this point? So at a very high VEB, if your IB is increasing, but IC is not increasing that much, or you can say that like after some time the IC does not increase too much larger. Like if, with respect to VEB, if you apply VEB potential, then IC does not increase very large. No, like if I keep on increasing VEB, then IC does not increase that much. No, like exponential relation is gone. Basically, I want to say that if you increase VEB, IC will increase, but IB would increase much faster at very high forward bias. At very high forward bias, what will happen to this guy is that I am not able to increase. Although I am increasing, the graph is always increasing. No, the graph is not decreasing. Although I am increasing, but I am not increasing by that much of amount. If they are increasing by 3 times, then I am increasing only by 2 times. So this guy is increasing lesser, but this guy is increasing more. So what will happen with beta? Beta will go down. So after a certain time, beta will start going down. So this is the condition of what? High level injection. High level injection means a lot of holes have come here. A lot of holes have come here. That means a lot of recombination would start taking place. A lot of recombination will start taking place. That means a lot of electron has to go. That means base current would increase. But at high level injection, the collector current will not be increasing by that large of amount. The collector current would be increasing, but increasing slowly. So here I have made 2 arrows. Here I have made 3 arrows. So IC is increasing lesser, but IB increasing so much more. That means effectively your beta will come down. So this is high level injection, high injection. At high injection, this will happen. So this is the graph of beta versus IP, beta versus IC. Okay. Another graph would be there, beta versus doping concentration. That graph we would see, but before that we need to understand some basic semiconductor physics. I hope this graph is clear to you. Beta versus IC. If I increase VEB, IC, IE, IB, everything would increase, but initially IC would increase very drastically. That's why beta would increase only. But after some time, what will happen? Because of high level injection, IC will not increase very drastically, but IB will start increasing very drastically because of higher recombination. Then what will happen? Beta would eventually come down. Okay, this is beta versus IC plot. Fine. Now beta versus doping concentration plot we need to see, but as of now forget about bipolar junction transistor. We are going to study basic semiconductor physics. So in basic semiconductor physics, we saw that we are having conduction band, we are having valence band. How these energy bands were created? Do you remember? Do you remember how these energy bands were created? So when your silicon atoms were far away, there was only one energy level, right? This kind of plot we made, energy versus distance. But as they started coming closer, what happened? Because of the interaction between them, they had to get separate rooms. And this particular room only we were calling as energy band. So when they were far away, there was no interaction. That means they were having only one energy level. But as they started interacting with each other, they split into energy bands. So previously energy level, just as they started interacting with each other, they split into energy bands. So this was happening when silicon atom came near to each other. Now if I am doing moderate doping or high doping, then what will happen? I am doing the high doping of donor atoms. So if you do the doping of donor atom, then there is a donor energy level which is created just below the conduction band, right? And what is your energy gap? What is your band gap? This is your band gap. What is the meaning of band gap? Lower level of lower energy state of conduction band and higher energy state of valence band. Whatever the difference is there, that is known as energy gap. But if you do so much of high doping, if you do very high doping, then what will happen? A lot of donor atoms would be there. Now those donor atoms, their free electron is sitting here, right? Now if a lot of donor atoms are there, they will start interacting with each other. If a lot of donor atoms are there, they will start interacting with each other. Because of this interaction, what will happen? This energy level will be split into energy states. Because of this interaction, this energy level, this donor energy level will be splitting into energy states. So this is how it will be splitting. Along with that, because of higher doping, this will move upward as well. Because you know that more doping, it will be more nearer here. So this will move upward as well. So what will happen is that these split energy state can get into conduction band as well. Like previously, you know that conduction band, below level of conduction band and this donor energy level, both are separated. But since a lot of doping you have done, these donor atoms will start interacting with each other. Because of this interaction, energy level will be split into energy state. So effective energy state would become this one. Like this would become your effective conduction band. Basically, your conduction band and donor band, they are overlapping with each other. So this has become your effective conduction band. So previously this was my energy gap. So now effective energy gap would be this much. This is after high doping, very high doping. What I am putting? Very high doping, or let's just put D only. So if you do the very high doping, the donor atom or the acceptor atom will start interacting with each other. If they start interacting with each other, their donor energy level will split into energy states. So effective conduction band would become this much. That's why your band gap has reduced. So in moderate doping or in high doping, whatever the band gap was, that was higher than the very high doping. So if you dope very high, then your effective band gap reduces. What does that mean? Do you remember Ni value? A naught. If Eg increases, Ni decreases. If Eg decreases, Ni increases. If Eg decreases, then what will happen? Ni increases. So if band gap has reduced, then your intrinsic carrier concentration will increase. Sorry, if it has reduced, then it will increase. So whatever the intrinsic carrier concentration I was having here, that would be lesser than this intrinsic carrier concentration. So based on that, we will solve a numerical, and then we will understand what will happen in our BJT. So let's solve this particular numerical, but before that, let's read out the theory. When doping becomes extremely high, the donor atom sits so close to each other that their original discrete donor energy level begin to split and spread out, forming a small donor band. As the doping increases further, the donor atoms come even closer, causing this donor band to widen and move upward towards the conduction band. Eventually, donor band merges with the conduction band and at the moment of separation between the valence band and conduction band effectively becomes smaller. That means the separation between valence band and conduction band have effectively become smaller. That means the band gap has become smaller. In other words, the band gap has shrunk because the conduction band edge has been pulled downward by the merging donor band. Whole scenario, everything is crystal clear, right? So what we are studying basic semiconductor physics as of now. We have forgot about BJT. What we are studying basic semiconductor physics. So in basic semiconductor physics, this was our conduction band, valence band, energy gap was there. But if I increase doping to a very, very high level, then donor energy level split into donor bands. Effectively, the gap between conduction band and valence band has reduced. Because of that, the band gap has reduced and your Ni value has increased. Why is that so? Because at moderate doping, my Ni square was A naught e to the power 3 by 2 Ni square we are talking, no? E to the power minus Eg by Kt. Now what will happen? It would become e to the power, in place of Eg what I will put? I will put Egd. So can I say my Egd is nothing but whatever the Eg was there minus delta Eg? Say yes or no? Whatever the Eg was there minus delta Eg. So Eg minus delta Eg, that would be my Egd. What is this delta Eg? This is your delta Eg, right? This is your delta Eg. Okay. So Eg minus delta Eg I can write down here. So here what I will write down? Eg minus delta Eg by Kt. So Ni square D I will put. Ni square after doping. So that is coming out to be, from here delta Eg you can take outside. So what you will get? Ni square e to the power delta Eg by Kt. This is something you will get. So e to the power minus Eg by Kt, e to the power delta Eg by Kt. So this is what you are getting. Previously, whatever the concentration I was having, multiply with exponential of delta Eg by Kt. So let's solve a numerical. This kind of numerical can come in your examination as well. And what will be the impact on our BJT, that also we will understand with respect to this numerical. Okay, so let's get started. In the intrinsic silicon, Ni value is 10 to the power 10. Band gap is mentioned 1.1 electron volt. Silicon is doped with acceptor atom of 10 to the power 18. So this was the initial scenario. And acceptor atom is 10 to the power 18. Still the band gap is remaining same. Okay. So in this particular scenario, what is the number of electrons in p-type semiconductor under equilibrium? That would be 10 to the power 20 divided by 10 to the power 8. That would be 10 to the power 2 centimeter cube inverse. When the doping is 10 to the power 18. But now when the doping has become 10 to the power 19, the effective band gap has become 0.9 electron volt. So at this time the band gap was 1.1 electron volt. But now when you have done the doping of 10 to the power 19, then this band gap we are getting. So Ni value now is not equal to 10 to the power 10. So Ni value after doping, that has changed. So what will be the Ni value after doping? So Ni value after doping, Ni square value after doping, that would be Ni square before doping e to the power delta Eg by Kt. I know that this value will increase. So what was the previous value? That was 10 to the power 20 e to the power delta Eg. What that would be? Delta Eg would be 0.2 divided by Kt, 0.0259. So when I solve it, what value I am getting? 2.257, 10 to the power 2.257. So this is your Ni square we are getting. Ni square after doping. So 2.257 into 10 to the power 23. This much Ni square we are getting. So here, this was my minority carrier concentration. No? This was your minority carrier concentration under equilibrium when this was my Eg value. Now what will be your minority carrier concentration after doping? After very high doping, what will be that value? That value will be Ni square after doping divided by Na. So Ni square after doping, that has become 2.257 into 10 power 23 divided by Na, that is 10 to the power 19. So what answer you will get? 2.257 into 10 to the power 4 centimeter cube inverse. What do you see? This was your minority carrier concentration. Now the minority carrier concentration has increased. What you expected? Ideally what I expected, sir, 10 to the power 20 divided by 10 to the power 18. So here I am getting 10 to the power 2, and here I should get, sir, 10 to the power 20 divided by 10 to the power 19. I should get 10 centimeter cube inverse. Here I am getting 100 centimeter cube inverse. Here I should get 10 centimeter cube inverse. This should be my electron concentration. But after doping, you can see that electron concentration has increased, not decreased. Why is that so? Because at a very high doping, your band gap started shrinking. Your band gap has shrunk. That means band gap has become lower. So intrinsic carrier concentration has increased. If intrinsic carrier concentration decreased, then your minority carrier concentration will also increase. How intrinsic carrier concentration has increased? In this manner it has increased. Because band gap has gone down, that means it has to increase. How much band gap has gone down? By 0.2 electron volt. So Ni square, whatever the previous Ni square I was having, e to the power delta Eg by Kt, 0.2 divided by 0.026, 0.0259, then this is the answer we are getting. Based on that, we can see that my minority carrier concentration has increased. So can you think what will happen in our BJT? So what we need to see? Emitter band gap narrowing. This particular concept we need to see. So what I am doing? Someone said that if you dope it very high, then what will happen? More and more holes will go here. More and more holes will go here. That means you will get more and more current. That's why I started doping it highly. But what I did very high doping. I did very high doping. I did the doping of 10 to the power 19 centimeter cube inverse. Because of that, what happened? This concentration got increased. This concentration got increased to 2.25 7. This concentration became 2.257 into 10 to the power 4. Now what will happen, you know, holes will be going here, that would generate IP current, and electrons will be coming here, and that would generate INE current. Now at the edge of depletion, what will be your electron concentration? That concentration, do you remember that this formula? Np naught e to the power whatever the forward bias you have applied by Vt. This would be your electron concentration, and this electron concentration will be increased now. Why is that so? Because this value, which is your Np naught, this has increased. This has increased. So this concentration also will increase. That means even if this is N plus only, but this is P plus plus, but because here you are having more number of electrons, because of that this concentration would be more, because this was the formula. No, I hope you remember this formula, Np naught e to the power V by Vt at the edge of depletion. At the edge of depletion, like first we used to draw the depletion region, then we used to talk about the concentration. So this formula was Np naught e to the power V by Vt, and this formula was Pn naught e to the power Vb by Vt. So all this derivation explanation we have seen. So here the electron concentration has increased. This value has increased. So what I am saying is that at the emitter junction, electron concentration has increased. And if that has increased, what does that mean? Your INE value has also increased. Are you able to understand this point? That means this value remains the same. Like whatever the Na value that was there, Na value is not changing. Doping 10 to the power 19, this is not changing, but this has increased. If this has increased, that means INE has increased. What about the base transfer factor? That remains same, because IP is same and IPC is also same. So no change in the base transfer factor. This remains same. Sorry, IPC was, this was IPC by IP. This remains same, but if this value has increased, that means this value has gone down. If this value has increased, this value has gone down. What was your alpha? If this value has increased, that means this value has gone down. That means alpha has gone down. And now what is the relation between 1 by alpha equals to 1 by beta plus 1? Both are proportional to each other. That means beta will also go down. So only one liner you can remember, at very high doping, beta will decrease. Why it will decrease? This is the explanation. Okay. So basically the thing is, two graphs of beta are important, because what I feel is that these questions are not asked yet in the GATE examination. They did not ask these questions. So that's why these questions can come up. This is the beauty of EDC, that if you do anything in very huge amount, like here I try to increase IC in a very huge amount, then started decreasing. So like in EDC, all the devices has some limit. If you stay in your limit, then I will behave the way you want. But if you get out of the limit, then they start behaving in some different manner. So always take care. If any kind of graph is coming in EDC, like if they are framing up a good question paper, a standard question paper, if they are setting up, then surely one graph would be there in your EDC question paper. Like in your whole question paper, one graph would be there from EDC. Always they ask one good graph if the question paper has been set up in a good manner. So when they are asking these kind of graphs, you always take care one thing, that at very high thing, like it can be at very high voltage, it can be very high current. So something, if it is very high, then they can change the nature. Only in EDC, not in other subjects. Only in EDC, at very high, it could be doping, it could be current, it could be voltage. At very high doping, at very high current, at very high voltage, the nature may change. You expected that it would rise linearly, but got decreased. Do you remember this curve? Mu versus temperature will rise and then decrease. So a lot of curves you will get in this manner. Did you notice this particular thing? Right? So this is what I was saying. So similarly here as well, from all this discussion, whatever that discussion we have done, what did you see? That at very high doping, beta decreases. At very high doping, If I say in one line, what will happen? At very high doping, from where he started, at very high doping, what will happen? Donor energy level will split into bands. They will combine with the conduction band. Then the effective band gap will decrease. Effective band gap will decrease. Then Ni value will increase. Since Ni value is increasing, then minority carrier concentration will increase. Since minority carrier concentration is increasing, then this particular concentration at the edge of depletion, the concentration of electron will increase. Because of that, INE value will increase. If INE is increasing, then emitter injection efficiency is decreasing. Base transport factor remains the same. That's why the value of alpha decreases. If value of alpha decreases, then you know that alpha and beta are having same nature, so value of beta decreases. So all the discussion, whatever that we have done, we could have said in one line only. Okay. So at very high doping, beta decreases. So what kind of graph you will get? So initially, beta will increase only. If doping increases, then what will happen? More doping, more current. More current means more IB current. Basically, increasing the doping is proportional to increasing VB only. Doping increases is proportional to increasing VB only. So initially, what kind of VB graph I was getting? This kind of graph I was getting. Increasing the doping is proportional to increasing VB only, no? If I dope it more, then more and more holes will be there. More and more holes will be going here. More and more recombination will take place. IB will also be more. Along with that, more and more holes will be swept away as well. So because of that, more IC, more IB, IC will increase in more amount. That means beta will increase. So initially beta will increase, but if you dope it very high, then it will start decreasing. So this is the graph of very high doping. Very high doping. Okay, like actually beta will drop down drastically. Usual value of beta is 100, but at very high doping, what will happen? Beta will become some 0.01. This much it will go down. Why is that so? Because everything is happening exponentially, no? You can see carrier concentration is changing exponentially, e to the power something. All the things are happening exponentially, right? This will also change exponentially then, because this is changing exponentially, so this is also changing exponentially. So this carrier concentration will also change exponentially, then this current will also change exponentially, this will also change exponentially, alpha will also change exponentially, beta will also change exponentially. So actually drastically down it will go. So better I should make at very high doping this kind of graph was there, and then drastically it will go down. Okay, so like at the fabrication part, these kind of things are very important. When you fabricate any device, then these things are actually very important. So what I feel is that they can ask these kind of questions in the examination, because these plots on beta, they never asked any plot. Okay, these non-ideal plots also they did never asked. In PN junction, when we studied about diode, there also we draw non-ideal plot, right? You remember those non-ideal plots for forward bias. So first I saw this kind of a curve would be there, then exponential would be there, and then 4 effects we saw, 4 kind of region we saw, region 1, region 2, region 3, region 4. So those plots are also not asked. So what I feel is that they can be asked in future examination. Okay. Now last topic is left, carrier concentration plot we need to draw. So for PN junction forward bias, can you draw this was your forward bias, this was your reverse bias. Can you draw the concentration plot? Yes sir. If I make it P plus, and here I make N plus. Okay, fine. So if I make it P plus, that means more holes will be injected here. So this concentration would be high and this concentration would be low. Or you can think that if it is P plus, that means lesser number of electrons are there. If lesser number of electrons are there, then this concentration would be low only. So this kind of plots you are getting, right? These plots we have seen. And this was your equilibrium condition. Here also there was some equilibrium condition. This is the N plus I am making, so this guy would be lower, right? Since this is N plus. So in reverse bias, what kind of plot we saw? This kind of plot we saw. So similarly for BJT as well, we can draw these kind of plots, but we need to combine both of them. Forward bias and reverse bias. What is our scenario? P plus plus, N plus, and P. So here this will be my concentration, like very less concentration would be there, very less electron concentration would be there. So now you know that this junction is forward bias and this junction is reverse bias. So this junction will say that I will follow the characteristic of forward bias. That means this kind of a concentration plot I will get. But what this guy will say? This guy will say that I will follow this kind of curve. So here this is fine, here also this is fine, but here you need to combine both of them. So this is saying that I will decrease and this is saying that I will go to 0. So what kind of effective, what kind of curve you will get? Effectively the curve will go down to 0. Basically I am joining both of the plots. Is that clear to you? Again let me repeat. Forward bias is saying that I want to draw this kind of plot. This guy is saying that I want to draw this kind of plot. So join both of them, that's it. This guy is saying that I want to draw this kind of plot. So here this kind of plot we will get, here this kind of plot we will get, here I need to join both of them. So after joining roughly around this kind of plot I will be getting. White color of pen if I use. But this will be actually, this width is very small, no? This width is actually very small. Base width is actually very small. So this will almost look linear. Almost it will look linear. So what I can do, I can make it look like linear. I hope this concentration plot is clear to you. Not very tough to understand. So whatever the kind of biasing is there, based on that you need to make it and you will be able to understand everything. What about this one? Forward bias here and forward bias here. Okay, both forward bias. This guy will say that, and don't forget this is P plus plus, this is N plus, this is P. So they will say that this kind of plot, they will also say that this kind of plot. But what do you think, what will happen inside? So here there is no issue, no? On this side there is no issue. This kind of plot you will get, no issue there. And here also there is no issue. This kind of plot you will get. But inside what kind of plot you will get? Inside you will get this kind of plot. Why is that so? Just think about it. Like this guy is also saying that you need to draw this kind of plot and he is also saying that you need to draw this kind of plot. So eventually this kind of plot you will get, but why this point is at higher potential, why this concentration is higher than this concentration? Because here both are injecting the holes, no? This guy is also injecting the holes and this guy is also injecting the holes. But this guy will inject more holes, this guy will inject lesser holes. So from here 2 holes are coming, from here 1 hole is coming. That's why this concentration plot is there. Is that clear? And now more things we can discuss. That why this point is larger than this point. This is P plus plus and this is P, right? So actually this is wrong. This has to be larger, no? Right? So that is wrong. Basically this would be at more. This is P plus plus, that means here concentration is low, no? How this particular point is decided? This is your NP naught e to the power V forward bias divided by Vt. So here NP naught value, this is your NP naught value. Here this NP naught value is lesser. That means this point will be at lesser height. And here this NP naught value is more. Because this is P plus plus, no? This is P. So if this concentration is higher, that means this point will also be higher. I hope you are able to understand. Or if you are not able to understand like why this point is higher, why this point is lower, then simply forget about it. Just remember the kind of nature. The kind of nature, making the kind of nature is actually very simple. How will you make this kind of nature? That is very simple. Why it is very simple? Because what you will do, you will just combine both of these graphs. Forward bias, forward bias, forward bias, forward bias. Just join them. Here if I need to make, what will happen? Reverse bias, reverse bias, reverse bias, reverse bias. There you go. This kind of graph you will get. Right? Again let me repeat. Both are reverse bias, no? Reverse bias means this kind of curve I should get. This kind of curve I should get. So if you join both of them, this kind of curve you will get. So simply you need to join. That's it. Okay? So what you will get? This kind of curve here, this kind of curve here, this kind of curve here, and this kind of curve here. So this will be your cutoff region, where this is reverse bias, this is reverse bias. So these two kind of plots are being joined, that's it. Forward bias, reverse bias, so this plot, then this plot is being joined, and here. So this kind of plot we got. For saturation mode, both forward bias, so this kind of plot we got. There is something called reverse active. That means emitter junction is reverse biased, but collector junction is forward biased. So forward bias will say that this kind of plot should be there, and reverse bias will say that this kind of plot should be there. So simply the opposite of this plot. Simply opposite of this plot. So what we will see? Here this scenario, here this scenario, and here nearly linear graph we will get. So minority carrier concentration here will be lesser only, no? So yeah, this plot. What we are drawing? We are drawing minority carrier concentration. I hope you remember what this was, minority. What we draw? We always draw minority carrier concentration. If this was your p side, so what we were drawing? We were drawing the electron concentration. If this was n side, what we were drawing? Hole concentration. If this was your p side, what we were drawing? Electron concentration. If this was your n side, what we were drawing? Hole concentration. So we always draw minority, right? Minority carrier concentration. Because in the majority carrier concentration, nothing much happens. Whatever that happens with minority carrier concentration. And it is true in all the domains. Whatever happens, that happens with minority only. Or second majority. Look, don't take me wrong. I'm not going in any other direction. Okay. I was not going in any other direction, just to make you realize that, like, when you go into USA, so like I never went to USA, but do you really think that Indians are respected there? They don't respect Indians there. Okay. It might happen that this video will be watched by some USA student as well, for sure, because I have some USA students as well. So they will also be watching this video, but they also know that, like, Indian students there, like, they are not treated in a good manner. It happens. Like, USA is a well-educated country, no, but still we are minority there, so we are not treated in good manner. So that's why I took this example. So yeah, so minority carrier concentration plot we are drawing. So this kind of plot we will make. Okay, and like, I hope you are able to understand that why this graph is going upward, because you know that this is less doped, this is more doped. So if this is more doped, that means hair concentration would be lesser, but hair concentration would be larger. So these lines also you will be able to draw, right? These lines you will also be able to draw here as well. Like, this is your p plus, no? So this line should be somewhere here. If I make this line should be somewhere here, and if you make this line is somewhere here. So this line will surely be above, because this is p and this is p plus plus. So what is the meaning of p plus plus? P plus plus is more doping. More doping means lesser minority carrier concentration, lesser minority. Like, this is like New Zealand. In New Zealand, most of the people are there from New Zealand only, but this is like USA. In USA, a lot of Canadians are there, a lot of Indians are also there, a lot of people are there, right? Okay, so these lines also you will be able to make. Same goes for this one as well. This concentration and this concentration. So one time, one question have been asked on these concentration plot. Like, simply you draw the diagram. Like, diagram was given, they asked what kind of a region of operation. Like, they asked the region of operation. I guess this diagram was given, so it was active region of operation. So they draw the minority carrier concentration. Based on the minority carrier concentration, they asked you which region of operation we are currently working on. So this was active region of operation. So this is the end of a bipolar junction transistor. I hope you enjoyed it. Not very important. Bipolar junction transistor is not very important, but still, like, if they want to frame good one question, they can surely frame it from here. So whatever that I have taught, that is enough. Now, if you go to PYQs, there you will find one question. There they will ask you the ratio of beta 1 by beta 2. This kind of ratio they will ask. Okay, and they have given the concentration plot in this manner. So this particular topic is taught in IC fabrication, okay, and this has been removed from the syllabus. So in BJT PYQ you will find this kind of question and you will feel that, sir, we did not cover this particular topic, but that is there from IC fabrication. It was asked in 2020 as far as I remember, but now this has been removed. So only this PYQ you will not be able to solve. So you will drop that particular PYQ, although that PYQ was also became empty only. That was marks to all because they did some error there. Okay, so that was marks to all, but when you solve the PYQs, drop this particular question if you ever see beta 1 by beta 2, because that has been removed from the syllabus. But it will feel like that, sir, it is there in our syllabus only, but you did not cover it. But it will never happen that if something they are about to ask or something they have already asked, it will surely be there in our notes if it is there in our syllabus. If something is out of the syllabus, that I will not cover. So this PYQ you will not be able to solve. You can drop this particular PYQ. Apart from this, everything you will be able to solve. So yeah, this is the end of bipolar junction transistor. Next we are going to start MOS. Okay, MOS cap and MOSFET we will start. Okay, yeah, thank you very much. Happy